So who?
Is William here?
I don't know.
Someone else? DNS OARC update?
Oh no, it's gonna be Keith.
Yeah.
Welcome back, everyone. Well, for those who enjoyed the lunch, I'm sure you liked it. And kudos to guys who arranged it, Dinesh and Keith and whoever else. It's pretty good. William couldn't make it here, so the infrastructure update will be delivered by Keith. Keith.
Thank you, Mehmet. Just give me a second while I update these. Okay, good afternoon. It's me again. It's one of the two main OARC staff members. William sends his apologies. He was unable to travel for some health reasons beyond his control. Bear with me a second. So I'm going to share with you an update about all the work that he has been doing on our systems. Before I started, I noticed one or two people wandering around the room who do not have name badges, which suggests that you didn't register. And there's absolutely no problem with that. It's an open workshop. We're very welcome to see you, but we would like to know who you are. So if you didn't register and don't have a badge, please see Dinesh at registration or help yourself. Okay, so systems. What has William been up to? To recap, there's a bunch of different things that we do with our systems, quite a lot for the size of the organization. Obviously, the crown jewels, as people mentioned, is our data archives. And then there's a bunch of services that we provide, which effectively are public services. There's the mailing list, there's the websites, there's various database servers that support the data that we have, and also these services. And then there are public services like Open DNS validating resolver, the top level domain zone transfer service, DSC, don't probe, and yeah, a lot of other bits and pieces. And then there's the actual capture systems which receive and process the data, DSC and DITL being the most important of these. And then there's all the stuff that we need to manage our infrastructure. And then there are some monitoring systems that we have, in particular TLDmon, I'll be saying a little bit more about in a minute. And we've also inherited AS112, the RFC 1918 DNS query black hole sponge, which William has always been very active with. OARC's also been involved, so we're doing some stuff for that as well. So much of what William has been doing over the past year is taking all of the above and migrating them to new hardware with current operating system releases. That's been the unpicking of a considerable hairball. There's all kinds of dependencies. A lot of stuff was just on that one server, which we call IN1, which is this ancient Celestica server. We've basically managed to unpick all of that, put it onto separate services, except for the mail system. And guess what crashed last night? So I apologize that from an end user point of view, it would mostly be the mailman mailing lists that you missed. But William, it fortunately gets up early in the morning and was able to fix that. But that machine crashes maybe once every 6 weeks, which is certainly less frequently than it used to crash because we've migrated everything off. So there's still one or two things that need to be unpicked and migrated, but I hope in the next month or two we'll be done and we'll be able to toss that thing in the dumpster. We split the stuff that was running on IN1 into two new servers, one running Linux, one running BSD. One of them is all the public, all the service-based stuff. Another one is basically research and analysis-based stuff. So things that we need in order to run the organization are on IX1. IX2 is what we do to provide services to you, our members, and the other research and analysis work. The TLDmon project, which is basically a Nagios instance that monitors various properties of all the top-level domains, has been migrated from a FreeBSD box to a Linux box, and William's done quite a lot of work to revitalize that. Although those notifications go to ICANN, if you're interested, then there's more notifications that we can send to you. And obviously, with all the new GTLDs that are being inserted, the number of domains that is handling is significantly increasing. And then there's the zone file repository. A lot of the larger TLDs allow us under their terms to gather a zone file copy. We archive these. We don't have a lot of people using them, but again, it's one of these data assets that we have built up over time that's probably quite unique. We have various mounds of data, quite a lot of databases, which essentially is not the major services like Ditto and DVR and DSC. Where does that stuff go if the larger file servers that we have are the most important? As I mentioned yesterday, we got 6 Sun X4500s. They still got a bit of life in them. So one of them is being used for now to host this OARC internal data. Another one is basically some spare NFS capacity because last year we got some historical URZ data from the RIPE NCC, so that's proved a useful place for that. But there is a longer plan for storage consolidation. We still run this lab. It's been used for various projects over the years. This was the original NSF grant that the work funded. It's still viable. It's still a useful collection. Some of these were being used as intermediate Ditto capture boxes, as spare capacity when we're doing the Ditto run. DSC, again, William has pulled that out of the nosedive that it was in. But the problem was it got into such a mess that a lot of people stopped uploading DSC data to us. So if you were uploading DSC data to us in the past and you're interested in doing it again, we'd very much like that. The whole future of DSC is a discussion that needs to happen. For now, it's in a much more stable shape, and it would be nice to start getting more data for it. Also, this was mentioned last time, but no, I think this was an experiment that started last time. There's something called Grid FTP, and we actually managed for the DURZ data from the RIPE NCC to ship 14 terabytes of data across the Atlantic on the net without having to courier hard disks or anything weird like that, using this Grid FTP light. So thanks to Inigo at the NCC for doing that. We may well use that technology in the future to replicate our data. The Jabber server was painful. If anybody knows of a Jabber server that doesn't run, that isn't implemented in arcane programming languages and is a nightmare to configure as a consequence, I'd love to know. JabberD just seems to be the least of the worst. There's various bits of state that seem to be in different places, and you can't get one to override the other. But eventually, we probably did lose some state in terms of chat rooms or arcane permissions in the chat rooms or something like that. But we did manage to get it migrated over to the new server. We've also there are 2 servers. We've basically managed to make them more resilient rather than just doing DNS round robin, hoping for the best. There is actual proper database synchronization between the 2 servers and the cluster. However, one of the servers is on the west coast of the US and the other on the east coast of the US. And it wasn't actually clear until the documentation was dug into that JabberD clustering isn't supposed to be done over multi-time zone latencies. They're supposed to be within data center. So the fact that it works at all is probably because they're on the same continent. Whether there's a better way to do that or not, I don't know. We also received, as part of the VeriSign donation last year, and also NetNode have supported us on this, so grateful to both of them. The root ops like us to run a separate Jabber server, not on our own server, not even on a VM. It needs to be dedicated hardware. So we've now got brand new hardware in Redwood City and also in Stockholm, which is running a dedicated Jabber server for the root ops, which is basically there as part of their emergency response plan. But it is ring-fenced from all other OARC stuff because, as you're probably aware, not all the root ops are OARC members. Indico, we've been running that for a year now. We've been keeping track in terms of upgrading that. It's one of these things that's great to have, but it's not perfect by any means. It's an open source project that is funded development. It's funded by CERN, and it seems to mostly be a succession of interns that work on it, and sometimes that shows. Hasn't crashed this weekend so far. Okay, that's William's comment at the end. But in general, it works pretty well. It's slightly unuser-friendly, but it basically has allowed us to run the meetings a whole lot better. We had to rewind the state a couple of times, but it's good to know that we have a backup regime which actually works when we need it in anger rather than something that we just keep backing up and never actually test. It's saved our skins a few times. Yeah, the database doesn't always upgrade. You need to sort of run the upgrade process 2 or 3 times for it to upgrade properly. But seems to be good. Hopefully we won't crash it before the end of this workshop. I think that we've sunk, I personally have sunk so much knowledge into driving the damn thing that I think we'll stick with it for now. But there's definitely a commercial opportunity for somebody out there to offer training courses and support contracts for Indico, that's for sure. Other migrations and updates, the DNS lab I mentioned, and the tender machine that manages that requires more documentation and it requires updates. That really needs some boots on the ground time in Redwood City, which William's not been able to do. And in theory, the SCSI disk needs replaced as well, although clearly with the cost of SCSI disks versus capacity these days, that will become cost ineffective at some point. Mail system we need to migrate, that's the last piece of the puzzle. We didn't think we were going to be able to migrate the Drupal website. It looked like what we did is we pruned a lot of it. There was all the workshop content we moved out of Drupal into Indico. So basically the archive for the old workshops is now all in a common format on the same server under Indico. That cleaned up the content of these meetings quite a lot. And then there was a bunch of other stuff which was actually internal documentation, which we moved off of Drupal into a regular MediaWiki site for internal use only, which massively reduced the amount of content between these two things. So it's only about 60 pages, which is manageable. It means that we can go to a website redesign consultant, which is in the budget, and they'll actually blow all of that budget. The Drupal has not been upgraded for so long that the theme that was implemented for the OARC website is no longer available for current versions of Drupal, which means that we can't just upgrade it to the latest version of Drupal. We actually wouldn't just lose look and feel, we would actually lose functionality from the website. So we were just going to leave that until we, having cleaned the thicket out, we were just going to leave that until we got to the point where we were hiring in the website redevelopment consultant, and then Heartbleed came along. So William spelunked into the Drupal caverns again, and he did actually manage to, in the process of upgrading the SSL libraries to something safe, he actually managed to get it migrated across to the IX1 server. So that's pretty good. It's probably just worth saying a little bit about Heartbleed posture. Pretty much everything was updated within about 1 to 2 working days of the vendor patches being available. We had 2 legacy things that we were stuck with. One of them was the Drupal site that I just described on the IN1 server. The other one was the Mailman, which is still on the IN1 server. At the moment, your Mailman accounts at OARC are subject to Heartbleed. We decided that this was an acceptable risk because all they are doing is protecting the mailing list subscriptions, and the passwords for that get sent out once a month in the clear anyway. What we would obviously not recommend that you do is use these passwords for anything else. Do not share your OARC Mailman password with anything else. We're going to tell you to reset your passwords, but at the moment we're just respinning the certificates on the site. So when we have completed respinning the certificates on the site, while there is no reason to believe that any passwords have leaked through this vulnerability, we're going to recommend what everybody else is recommending, which is change all your passwords. One thing that's slightly annoying is that there are a whole bunch of people, well-meaning people out there who run tools to detect Heartbleed vulnerable SSL sites, and all they do is check the actual version number. They don't actually check the fact that we've patched it, but the version number hasn't necessarily been increased. So it may look like it's vulnerable, but it's not. Collisions boxes, this was the donated hardware that I mentioned yesterday. These are the N3 and N4 boxes, significant 64 core processors, reasonable amount of storage, but more than the amount of the main data set of the other file servers for the digital services. Here is how the data is spread across the various file servers. These file servers are roughly being purchased on an annual basis, but we're nearly full. A data run can consume 10 terabytes. It can also consume less than that. It varies quite a lot. But basically, you don't get into the FS servers, but if you want to access the data side, the digital data for collisions or other purposes, we will give you a shell account on one of the analysis servers. Just send in your public SSH key, and then these are the machines that get access to the data. So we were running out of space. We thought, right, it's time to try something new, get more space. This will allow us to consolidate the data on a single server. Like I said, the cost of doing big data storage is a lot more commodity than it used to. So I started buying 4 terabyte desktop SATA disks. We just bought 20 of them. We, with the help of the IC Ops team, they have been inserted into a storage pod based on the Backblaze architecture. We haven't quite got to the point where we've commissioned that. William just got it live last week. So we're going to investigate that. It can potentially take 45 4 terabyte drives, so 180 terabytes in theory should see us into the future. But obviously there are issues about the cost versus lifetime of using desktop drives, and we're going to see how that works out. Some pictures of computers in racks, not very exciting, but you can see that this is the ancient Celestica on the top right, which we will shortly be ditching. Most of the file servers that we've got are based on Supermicro based architecture from IX Systems, and then these are the donated thumpers on the bottom right. So DSC, we already had members who wanted to upload DSC data to us, but they had too many nodes in their Anycast cloud and it wasn't scaling. What William has done working with some of the other members is found that those who were actually doing pre-processing of the data at their end before they submitted it, rather than letting us do the pre-processing, this scales a whole lot better. So if you're doing DSC submission to us, or you're interested in restarting DSC submission, definitely have a discussion with William about the actually doing the post-processing at your end rather than our end. But DSC is a project that needs complete reevaluation. It's been around a long time. I've seen many, many things that members have implemented in our house, which are just vastly more modern and functional. So that is a longer term discussion that we need to have. Bigger question, what is our data growth like for the foreseeable future? If, for example, we started gathering data during incidents, just how much could that be? Sorry, this slide gets slightly distorted in reformatting, but you can see that this is digital data over the 8 years that OARC has gathered it. There's a lot of variability in the size of the data set depending on who participates. It can be as high as 10 terabytes, but it can vary a lot. Sometimes we get extra data, sometimes we don't. But really we need to start buying servers that will last us 5 years into the future, not just one. Digital 2014, thank you all for everybody who participated and submitted data. We're pretty much done with the upload. Currently around 3, it says gigabytes on that slide. I know that it means terabytes really, which is actually smaller than the last 2 years. There was a mismatch with one contributor because of some personnel changes at their end. They didn't find out about the exact dates. We were a bit more secretive about the dates this year. We always try and keep that limited circulation because we don't want the data gamed, but there's obviously, with the name collision stuff, there's a lot more risk of gaming of the data and vested interests that might game it than there have been previous years. So we were a little bit more opaque, but that was actually, we did discuss that in the board, and that was actually a deliberate discussion. William has been working with Dwayne this week to do the post-processing of that data. I hope that within about 1 to 2 weeks, the 2014 data should be available to you as members. Another thing that's important is that William's been trying to crank the handle on the digital gathering and processing himself with minimal help from people who have done it before. That's flushed out quite a lot of issues and gaps, but the good thing is that we're finding out where these are. we're rectifying them, we're making sure we have all the pieces of software that we need in one place and making sure that that's also documented. So future considerations, what do we do with all this data? Old versus do we keep it all? Probably we do. We desperately need to store a copy somewhere else on the planet. Like I said, we're in discussions with one member who wants to give us more hosting space. Is it good where it is? And there's also better monitoring that we need to do. Making sure we get a feel for the network utilization. Part of the plan this year is we've purchased our own router, which we will use for make us more autonomous of the ISC infrastructure. That will help us actually monitor the data usage. We're going to upgrade our infrastructure to a 10 gig core between the servers later this year. That's in the budget, so we'll be getting some 10 gig switches and NICs so that we can improve the throughput between the internal boxes. William has written an infrastructure plan which he and I have been iterating. I have a draft of that with me, which is not been internally reviewed, but certainly welcome anyone who's interested what we're going to do with the longer term infrastructure plan interested. So we are where we are. A lot of this is to do with history and where we got to. We need to start having a little bit more future vision of where we're going to, what is the meaning of this, all the rest of it. You know, we hope we can build a reputation for research. Certainly the name collision stuff has increased our profile in that a lot. Well, it's interesting because William's background is in high performance computing and academic environment, and he says that a lot of what we do resembles what a lot of academic researchers do. So it's more of the same. So that's me channeling William. I'm happy to take any questions. I also may decide to punt these questions to William, who is online for Jabber at the moment. Hopefully that'll give you some idea of what we've been doing with our infrastructure and where we're going with it. Stefan, what did we break now?
It's about ODVR. ODVR has no IPv6 connectivity for now 2 weeks, 3 weeks, something like that, a long time. And I saw no mention of connectivity issues on the slides.
I don't know what the cause of that is. I'm not sure whether that's an issue on our end or an issue on the ISC end. I know that William is working on it. I apologize for that.
Because if the problem is lasts so long, it may be a good idea to modify the ODVR web page to say IPv6 down for the moment, something like that.
Any other questions? One more question. We have time for one more question. I guess not.
Okay, I'm here until Thursday and until Friday if anyone wants to ask me any detailed questions about the infrastructure. Thanks.
Thank you, Keith. Our next speaker. Christopher Baker.
It's so comforting to not be the only one who hasn't used Windows in a while.
That's what you need a Microsoft employee to develop with that. It's not? Okay.
Anybody know any good jokes? Requests?
For those who have baby, it's a beautiful, beautiful neighborhood.
You know what it is? It's the lighting fixtures. They really treat for the mood for that.
Yep. PDF, perfect. Let's do this.
I did develop it in PowerPoint, just so yeah, I was supporting the team. Thank you. Good afternoon, everybody. My name is Chris Baker. and I'm a data analyst at Dime. Also a keeper of dogs, a lover of the internet, and a hater of ne'er-do-wells. So this talk is about Namecoin. And you might wonder, okay, how is Namecoin really relevant to DNS OARC? Well, over Christmas vacation, I needed something to do because, as we all know, you can't just sit there and do nothing. And I started to look into that which is Namecoin. So before we get into it, there's kind of like a bit of weird background you need to build up to get people kind of interested and excited about the prospect. So first, we're going to talk about the year of the cryptocurrency. And I'm sure most of you are familiar about this, as earlier people made jokes about mining Bitcoin with spare machines. But essentially this year, all of a sudden there was this, I guess, rebirth and interest to the idea of taking stored compute resources, so CPU cycles and power, and putting them into these intangible units to be traded into the future. Now with these came the beautiful things such as the top left, the Hobo Nickel, in the middle, the Bitcoin, Litecoin, Coinye West, and Dogecoin. Now I'm not kidding. These things kind of matter in reality. So when Overstock.com decided they were going to actually accept this as a currency, some big numbers were exchanged there. And then all of a sudden, there's a NASCAR with the Dogecoin dog on it. So as trivial and humorous as this all kind of sounds, it's here and it's real, and we're going to have to deal with it. There's kind of like this weird background of people trying to figure out how you store work in these units and how you trade them in forward. We're not going to go too deep into that because, I think most people here are comfortable with the fact that we can do it well enough to have confused ourselves into accepting it as tenure. And if you think about it, this is really the greatest O-Day contest in the history of the internet, because if you actually find a 0 day in any of these, you get the currency. So if you have some spare time, maybe that's something to look into. So what is Namecoin and why is it important to us? So essentially what people started to think of is, well, there's this code base for doing decentralized transactions. You're decentralizing a database. So in Bitcoin forums and in IRC, people all of a sudden started to think of, well, what if we implemented the DNS here? Now, this is a really awkward reference to make because the only source of truth for it is an IRC log. But apparently back in 2010, a gentleman had mentioned, hey, we could do the DNS here. All of a sudden, Aaron Swartz, a big internet activist, picked this idea up because all of a sudden, you now have this potential way that you could take control away from the man that is ICANN. Just kidding, I have no problem with that. You're the man, Joe. There's this resurgence of having names that no one could take away from you, right? Because they're owned by the people. And of course, this enters into why this paradigm exists, which would be supported by Namecoin. So Aaron Swartz started to think this through, and he drafted the comparison to Zoko's triangle or Zuku's triangle, depending on how you properly pronounce that. And basically posed that you get to choose two sides of the triangle. You can't get all three. Now, again, the more when you research this, supposedly Nick Szabo has written some papers which refute that this is actually the case or the current standing with secure names on the internet. But Dan Kaminsky did a really good job in framing off these trade-offs in a visual manner. So as you kind of walk through them, you kind of have the onion model, which is like a really obtuse-looking, secure, decentralized, but not human-readable name, followed by a secure, centralized, human-readable name, because you're handing off that authority to ICANN to deal with. And then you have the decentralized version where enough people agree that name is belonging to that person at that time. So Aaron Swartz and Dan Kaminsky are going back and forth on internet forums about how this is going to work. And whenever you do something like that, you break it down to like physical meat space style narratives. So in this case, it came to be like a scroll. So we all have this scroll, right? Each of us is maintaining a copy of a scroll, and the scroll has a collection of lines. Now, we're going around and we're forming proofs, and we're saying, okay, person number 1 is establishing this with a key and a nonce, and this is where the whole notion of like stored work comes in, because you have to calculate how that's going to be cryptographically secure as more things are added to it. When you want to find what a name is, you go around and you find basically the person with the longest list, because they have the largest number of transactions centralized, and you can go back and kind of follow ownership of names through the list. And to publish a name, you basically tell everybody you know about the name and how it's going to work. So then, of course, what you have to do is you just have to justify how you're going to protect the names. So the definition here is, well, because you have to do so much work to add something to the list when you have the longest list, you have to have more computational power than a larger circuit of everybody else who's keeping a copy of the list to kind of sneak it in there. And then you also have to be able to replace everybody else's copy of the list. So at this point, this is still all very theoretical. Schwartz decides, okay, Kaminsky, take a shot at it. So Kaminsky responds, he points out a collection of flaws, as technical people do when they're going through an RFC or somebody's logical construction. And the funniest one actually comes down to failures in day-to-day use cases. So it turns out that reconciling transactions is hard. And I think anybody here who's ever worked in a database can agree that distributed transaction semantics are hard to actually implement in real life. So he comes up with a scenario where two people are trying to publish something at the same time, there's a collision, and eventually you have like a split brain scenario because somebody needs to choose which was first and what's going to be maintained in the list. Details, details, details. So the logic goes on, the battles go on, and eventually a group of people step aside and they say, okay, your ideas are great, we're going to implement this. And they start basically rolling out what is Namecoin now. This comes to be in, I guess, the greater world of the internet, in the special use domain names peer-to-peer systems, in which .bit kind of appears for the first time as a real thing on the internet that we all agree may or may not exist. This document gets some interesting reactions from people depending on how you fall in the existence of .onion, .gnu, and a few of the other non-regulated domains. But yeah, it's in there. They implement a wide range of records. And this is kind of interesting, again, from the DNS perspective, as to what they chose to implement. So based on the community, you have like a skewing of records specifically for Tor names, for I2P, but you also have all the classic R types that we're used to, including DNSSEC, which I thought was kind of funny because as people go along, there's been some criticisms about DNSSEC and its role in this weird and wild world of that which is .bit. So, as I mentioned, at Christmas I started to dig into this, and I was mainly curious about how people were using it, how it was being adapted, and where people were using it. So, funny thing, when people are doing this, the first set of tools that arise are basically taking the blockchain that's coming from .bit and breaking it apart and making bind zone files out of it. So a lot of the tooling and a lot of the name servers that actually exist right now and serve the .bit domain are running bind. So it's very easy to go out there and get a copy of the zone file. So the first thing you do, you take a look at the number of A records, NS records, and all that kind of fun stuff. One note, the reason here we're saying raw is the wildcard is separate from the proper name. So I thought about deduping them, but that just got awkward. You have to explain why you thought you needed to do that. So right here, just as a note of what the raw, I guess, means. Raw record count, so a measure of the number of unique addresses on the internet, the number of the net blocks, and the number of unique ASNs. Now, all these data points aren't that interesting alone, so you kind of need to fast forward and look at them in context of what things are looking like right now. So of course we have these pretty arrows to give you some context. And you start to notice there's this awkward drop-off. And you might start to wonder, oh, well, what's going on there? It seemed like things, it had a decent number of records before. Why are things falling down? Well, when you look through it initially, like any naming system, there was a massive land rush. People ran out and they registered all the single letters, double letters, triple letters, anything that might be useful in phishing or anything of that nature. And then things just kind of stopped. So then you might ask, okay, well, can we get some usage number for these? Well, it turns out the people who run the recursives for them do not want to share this data and are very protective of it. So it's kind of hard to get a proxy of how well is this being used. So country codes. I thought it was interesting that the US had one of the higher spreads here. A lot of this is due to the hosting providers that some of these IPs are pointing at. Similar with the other ones in the top areas. As you'd guess, Hetzner, OVH, and a few of the other maybe not well-liked hosting companies have some bruises here from these, and we'll get into that kind of later. And some of the surprising ones were who had these pointing into their domain space. I guess I don't really know why I'm surprised that they're there, but it's always interesting to see who has these resolving to their space. And then there's your expected hosting providers. So, implementation issues. Because .bit isn't in the root zone file, you have to go through some weird corner cases to access domains that are in the .bit space. So that means you're either installing a side plugin to your web browser, or you actually have a copy of the name chain local to your machine, or you're querying one of these .bit DNS servers. So the accessibility issues are heavily prohibitive. So specifically in the US, if you want to actually get a hold of these credits and not actually try to mine them, which it turns out is not economically a good idea. It's actually easier to go out and purchase them from an exchange than to rig up your own machines to try to mine them. So if you'd like to actually go out and purchase them, it turns out to access these exchanges, you need to send them a copy of your passport or log into a chat and hold up a picture of yourself and a license. I don't know about you, but I don't like sending my passport out to random people on the internet who are running strange cryptocurrency exchanges. So there's some weird barriers into like entering and transacting in this space. And when you look back at the history, there's kind of some fun points. So I don't know if anybody remembers, but when, you know, I guess it was around last December, there was this massive burst in interest for the cryptocurrency world. This is back when the whole Silk Road thing was going on and teenagers realized they could buy drugs there. And then people were thinking, okay, well, you know, if I can get these type, I can trade them for these and kind of like swatch them all around. So like, you know, like a Dutch tulip auction, there's that huge spike in value and then a slow dribble off as people realize the actual usage value of them. And everybody loves charts, so you throw in like a daily spread there to give an idea of like the volume and the pricing for them. Now here's why I got into this. So it turns out malware developers are awesome, and they think of really clever things to do with these side systems. And we only say they're awesome because they create the challenges that we need to fight in the world to give ourselves some meaning and understanding. So you ask yourself, well, how are they going to use this thing if it's so hard? If you have to have a browser plugin or if you have to pull a copy of the blockchain back to your machine? Well, it turns out there's a clever way within the Windows API to say, query this name server. So instead of actually configuring it on your machine, there's a call where you pass it a parameter and you say, instead of accessing this name server, hit this one. So they did that, and all of a sudden the Netcurse malware was now basically breaking new bounds and was in theory unsinkable. Now why is it unsinkable? You can't take these down. As long as the blockchain exists and everybody agrees that's where the name was, unlike traditional TLDs, there's nobody that has the power to remove it from the system. So it'll continue to live on as long as it can. But then, luckily, the blockchain itself manifests itself as a passive DNS system. And this is another one of like the secret beauties from like a nerdy data perspective, because when you want to go back and look at what something was, you can figure it out really clearly. So what I did when I actually got some Namecoin, I bought DNS OARC and DNS-OARC. And I configure them to point at the DNS OARC site, because that's what you should do with them, people. Right? So you can go into the blockchain explorer, and you can see, okay, well, you can configure the A record to point to this IP, blah, 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 really fun. But in the case of malware, you can go back and you can look at, okay, well, so this is one of the popular Netcurse .bit CNCs. So if you went to megashara.bit, you can go back and see all the different places and all the different IPs that it was once using for a CNC. And it's kind of built into the blockchain to always be there. And if you think about this in contrast for other different record types, there's a lot of ways in which having this persistent form of all the history of all the different records and having it be manifested everywhere where the blockchain itself is really cool. Now, granted, there's other issues with scaling when you're tracking the history of all these records as you move along, but. So then the bad guys realize that people have figured out what they're doing with it, and they start to just use it as an interesting signaling mechanism. So the CNC IP, which we were pulling back related to a .bit domain, is then just another key, which they're hashing with something else to find the real new CNC domain. Cat and mouse game, people figure out tactics, they change tactics around. Interesting, though. So we've talked a lot about like what bad guys are doing, and you always need to lighten things up at the end to give people a sense of hope and cheer for the future. So there's another group who's actually trying to think of novel things they could do to protect privacy when you have this distributed database. And one of those is DNS chain. Now, again, I don't completely agree with some of the authors' stances on some of the technologies that they're refuting don't solve these problems, but their perspective is interesting and should be considered. So essentially, the claims are that the certificate authorities don't offer you the privacy that you need, because in the end, you're relying on somebody else signing something else that somebody else signs for somebody else. And in theory, if you have this blockchain with a collection of fingerprints and pretty much whatever other data you'd like to put into it, you could then choose who you trust based on these configurations. So it's I don't want to say it's a simple system, but it's a transparent system for putting identity credentials into this distributed system and basically facilitating access. And the line I kind of liked was the trust only those you know versus trust a bunch of untrustworthy strangers. I thought it was a pretty clever marketing line. So this allows you to store identity information, fingerprints, pretty much anything that you might want to. They've written some APIs for it so you can integrate with websites. And eventually, as the cost gets cheaper, they're hoping to have it basically establish its own certificate authority. Now, they point out that some of these problems are solved with applications like convergence, which allow you to select which certificate authorities you'd like to respect and those which you wouldn't. But their notion is that you should abandon that system and you should go with a new system in which you are choosing who you trust completely. So actually, that I got through everything there, and I was wondering if there's any questions.
All right. Any questions? See online. Stefan?
Not a question, but a remark. It's true that you have in the blockchain the entire history of the blockchain. It's not the complete equivalent of things like DNS because you can have delegations. You show only IP address directly in the blockchain, but many people use a delegation, and in that case, the blockchain will not show the IP address and the complete history. So you still need passive DNS stuff.
Oh yes, yes, you certainly do. It's just I found it interesting the way that it was maintaining all the I guess passive DNS is the incorrect term to use. Maybe just the record history for all the domains or the record history for all the different keys. That's actually a good specification.
Any other questions?
Yes, another one in that case. It's more speculative. Do you think that the people who work in the domain name registry should prepare for a big change to find some other work?
No.
Or not yet?
So one of the things that's really interesting about this is I guess the lack of success in Boom, and it kind of shows the need, the buy-in that you need to have something like this become successful. So the idea that an individual user now has to figure out how to do all these configurations instantly cuts your target market down by a large amount. And if you think about some of the other news recently, which is telling people be really careful about the browser plugins you use, because it turns out people are buying those and using those to sideload malware into your browser. So there's a collection of things that kind of shade and take away people's potential interests into doing these sort of non-mainstream activities. I think there's also, though, an interesting side case where for hobbyists and other enthusiasts, it's a great area to explore, I guess, alternatives.
So Warren Kamari, Google, this is more of a comment than a question. There seem to be an increasingly large number of things that use sort of pseudo TLDs, or that make up the last thing. You had a list of, I think, 7, or at least the draft you mentioned had a list of 7. Myself and a few others, although I can't actually remember who now, have a proposal that there's be a real TLD set aside for this, or at least a real label reserved for this, .alt, and other things move under that, like .onion and .bit and stuff like that. Just a comment.
No, I think it's so when you read the special use domains paper, it's really interesting because from somebody without some of the, I guess, the proper history and how these things came to be, it's funny to think that people can just go out and do this, and then you think about, oh well, so now if somebody actually tried to purchase a register .bit, there's going to be all kinds of horrible collisions, just like all the other research points out. So yeah, that's great. Organization for the win.
Very interesting, right? Well, thank you very much, Chris. Next we have Aziz, but obviously now it all makes sense, with this presentation, Bitcoins, and Joe wanting 50,000 server. We kind of know what he's after with those bit mining. Right. Is something?
Yeah, I need to download the presentation.
I can now.
Oh, yeah.
Don't worry. You want the PowerPoint version?
There's a video of it. It's on the website.
Second, I think. No, it's-
PowerPoint,
oh, there we go.
PPTX.
There we go.
Download it.
Here's your mic. Oh, good afternoon, everyone. My name is Matt Thomas, and I'm a data architect and researcher at VeriSign Labs. And today I'm going to talk about detecting malware domains using DNS traffic. But before I get into the detection mechanism and the algorithm that we actually developed, I kind of want to maybe just set the stage and kind of give a brief overview of how malware is commonly set up out there, so we're all on the same page. So on the left-hand side of this figure, we have a diagram that pretty accurately reflects how malware is set up out there on the internet commonly. So on the bottom, we have our infected hosts, or our zombie PCs, right? And so for the sake of this conversation, let's assume it's a homogeneous infection. So it's the same piece of malware on all of these PCs. And at the top of this diagram, we have the botnet master or the bot herder, whatever you want to call him. And he, I guess, or she, is going to eventually want to send some commands down to these infected hosts to do some kind of nefarious event, right? Like kick off a DDoS or send the spam. And so that's where this middle layer of the infrastructure comes in, and that's the C2 servers, or the command and control servers. Now, the botnet master, he actually has direct control and access to these C2 servers. And the zombie machines down at the end, they're frequently pulling the commands from those C2 servers. Now, the botnet master at the top has obviously spent a lot of time, a lot of money, a lot of effort in making this infection go around the world. So they're going to try and do as many things as possible to minimize their takedown or mitigation from antivirus or law enforcement. So one of the easiest things for them to use is a domain name, right? You can think like statically encoding the IP address, and the malware on the bottom is just a single failure in the whole system. So this domain name on the C2 servers obviously provides a nice layer of indirection. But malware authors are getting a lot more clever. So instead of just using one domain name, they're constantly changing this domain name out on a frequent basis, sometimes daily, sometimes even hourly. And so this process is more commonly known as domain fast fluxing or domain generation algorithms. And so a domain generation algorithm is actually nothing more than a function that takes an input, which is almost always your system clock, date, time, right? And it returns a set of domains. Now that set of domains might be 1, it might be 10, it might be 100, and those domains might span one or multiple different TLDs. But there are a couple really cool aspects about this domain generation algorithm. First, the malware author obviously knows the domain generation algorithm, right? So he can precede that function with dates in the future to know all the domains that are going to be generated at any given date in the future. So that enables the malware author to be able to register a subset of those domains so that they can always be ensured that they're going to have a means of contacting these infected hosts down there, right? Now on the flip side, the second interesting part of this DGA algorithm is that we know that same algorithm is going to run on every single infected zombie machine out there. And at the same time, those hosts or PCs are going to generate the same set of domains. And after they do that generation of domain names, what are they going to do? They're going to perform a DNS lookup on them, right? And as you can expect, when you do a DNS lookup on a bunch of pseudo-random domains, the vast majority of that is going to come back as non-existent domain responses. And so that's really where our kind of research and motivation for this work stemmed from, was that we wanted to see if we could find common patterns between all of these infected hosts that are generating the same set of domains on a very specific time that are resulting in a large non-existent domain footprint. So in order to do that, we turned to one of the most popular pieces of malware out there. I know it's old, but Configure is still extremely prevalent out there on the internet. It infects tens of thousands of machines. The malware software itself has actually gone through numerous variants. I think it's up to like 6 or 7, maybe even more now. But luckily enough for us, there have been some really smart engineers that got their hands on the executables, and they reverse engineered the DGA algorithms. So now, as researchers, we know for this particular variant, on this particular day, this is the set of domain names that are going to be generated. So we can use that kind of as like ground truth to try and basically measure any kind of new detection mechanism that we're going to come up with. And so that's what we're going to use in this research that I'm going to present in a little bit. But to do our due diligence, it's probably better to just paint the general landscape out there and take a look at the NXD traffic in general from like a ComNet TVCC perspective, or TLDs that VeriSign's operating. So this is going to take a look at a multi-month collection of NXD traffic from ComNet TVCC, all TLDs VeriSign operates. And here we're just going to basically look at total query volume on a daily basis. As you can see, Com is clearly the winner here, right, where winner is the guy that receives the most garbage. And net significantly less, and the CCTLDs are pretty minimal relative to Com and net. But in addition just to like pure volume, we might also want to see like how many different distinct second level domains we're seeing. So here is the same study of time, but we're looking at the number of distinct second level domains. Well, you see the similar trend where Com again is the winner, receiving quite a bit, net significantly less, and so forth and so on. So I'd like to call out a couple of numbers right here. So we're seeing Com roughly seeing about 2.5 billion NXDs per day, and that spans about 360 million unique second level domains. Net's about a magnitude less, 500 million NXD requests spanning 60 million unique second level domains. Now the reason I'm pulling out these numbers is because it's important for us to start framing this in terms of developing a computational algorithm, right? Most of the algorithms that we're going to want to evaluate or build are going to have some kind of algorithmic complexity of something at least n squared or larger. So when n equals 350 million, you can imagine either you're never going to get your result back in the next 50 years, or you better have a whole lot of computing resources, right? So it's beneficial for us now to see if there's some kind of way for us to reduce n to a much more feasible number, especially if we want to do this in kind of like a real-time detection, because we know that domain generation algorithms obviously have a finite period of time associated with those domains. So in order to do that, we kind of inspected a little bit more of what these distinct second level domains are actually receiving. So this is a cumulative distribution function plot of the various TLDs, ComNet, CCTV, and here we're measuring the total number of requests a given distinct second level domain receives within a 24-hour period of time. I'd like to just also point out that the x-axis is actually in log base 10, so it's a little bit more difficult to read. But one of the interesting observations here is now the distribution for these TLDs seems to be all similar, right? As opposed to the previous plots that we showed on the volumetric sides where there was great difference between these TLDs. But the next thing we wanted to also do was take a look at the churn rate in these second level domains, right? Do we see this distinct second level domain coming day after day after day, or is it kind of a once and done or a one night stand kind of a domain, right? So what we did was we broke up this multi-month collection period into weeks. And for the given domain, we counted the number of days that had occurred within that given week. And again, here we're just taking a look at the CDF plot of this. So from this, now we have a pretty good description statistically of what it looks like from a ComNet NXD perspective. And we've learned that basically 95% of all the second level domains out there receive a very minimal amount of traffic, right? Less than 10 requests within 24 hours. And that there's an extremely high burn rate within the distinct second level domains. So now we can move on to compare and contrast known malware associated domains from something like the DGA of Configure and see how those compare statistically. So like I said before, we know exactly on this given day of time that a DGA like Configure is going to generate this very specific set of domains. So if we consider those domains on the day that they're supposed to be generated, day 0, the center of this plot, we can measure the DNS traffic for them. But we could also measure that set of domains days prior and days post, just to understand the traffic to that. But on their actual generation day, you can see the volume up there is tremendous, right? And even after and before, these domains are receiving quite a substantial amount of traffic. Now, just to make sure that this isn't coming from a few different sources, we also looked at the distinct /24s, right, to make sure the diversity of the request was pretty high. So on the actual generation date, you can see that these domains come from almost about 50,000 unique /24s. So this piece of malware is very well spread out over there. So basically from this, we've learned that a couple of interesting things, right? Despite a specific generation date, these known malware domains are receiving significant amount of traffic on days prior, days post, and obviously on the day of. So the more important aspect to take away from that is that these domains vary greatly from the average norm of NXD that we see. So now this means that we have a very simple way of just filtering our N down to a much more computational feasible number, right? We can do some kind of basic filtering saying, let's only consider domains that have, greater than some kind of threshold of traffic quantity, like 100 requests within the last 24 hours. So now N's down into the order of, a couple 100,000 versus 350 million. So now that we have that domain set reduced, let's start looking at how we're actually going to do the detection, and furthermore, the actual organizing of these domains that we do detect into some kind of meaningful hierarchy. So specifically, I'm going to talk about the detection and the clustering algorithm that we came up with. And within this, I'm going to focus on two specific questions. So the first of which is, how similar are these traffic streams to each other? And by that I know we have the domains to be generated on a specific day. And if domain A and that received a set of requests from these 50,000 unique /24s, and domain B received a bunch of requests from other /24s, how similar are those two sets? And then using that similarity, question 2 is, can we use that similarity to group these different domains into some kind of more meaningful hierarchical entity? So obviously all of this is revolving around the concept of similarity. So I need to really speed up, sorry. Similarity function is just a way to quantify the similarity between two groups. But basically what we end up using is the Jacquard index. I'm sure many of you have used that. Mathematically, it's nothing more than the size of the intersection of sets A and B divided by the size of the intersection or union of sets A and B. And obviously this is going to return a range-bound value between 0 and 1, which a Jacquard index of 0 would mean that these two sets have absolutely nothing in common. Index of 1 would mean the two sets are identical, right? So using this concept, we are now going to measure the pairwise similarity for all the domains on their actual generation date. So in this CDF plot, let's first look at the black series, right? This is the set of domains on the actual generation date. And we measure the pairwise similarity between those. And as you can see in that distribution, these domains have like an average similarity of something greater than 90%, which is pretty crazy when you start thinking that these domains have more than 50,000 unique /24s hitting them. You're not just going to get this randomly out of the blue when you just compare two NXDs with that kind of traffic. Obviously, it's being caused by the malware underneath. But also, we can take a look at the day pre and the day post and also measure the similarity of those traffic. And that's actually the red and the green figure there. Now, the similarity measurement isn't as high, but it is still substantial, right? It's in the 70s to 80s range. So now that we know that using similarity, it's a great way to possibly start detecting these malware-associated domains, we need to start putting them into some kind of meaningful context. And so this is where the clustering algorithms are going to come into play. So this figure is actually showing quite a bit, but let me try and explain it as quickly as possible. On the X and the Y axis, we're taking a subset of domains from configure A and configure B, two variants, and the shading of the cells reflects the similarity of the request for those two domains. So red cells means that those two domains have very little in common. Yellow means that they have very high similarity. The white diagonal means that they're identical. And you would imagine that white diagonal to be on the diagonal of the similarity matrix because anything measured against itself should always be equal to 1, right? So what was interesting is that these clusters naturally form two distinct groups just off the similarity measurement. But when we start applying techniques like single linkage clustering or hierarchical agglomerative clustering, which you can see on the dendrograms on the side, we can use minimum similarity thresholds to put these into distinct clusters, or basically define clusters associated with very specific pieces of malware without even running or knowing any knowledge about that piece of executable or malware ahead of time. So I know this is very vague, and how do you apply this? So I tried to come up with like a visualization technique. So if you can put on your crazy hat with me and imagine a 3D space, right, outer space that's completely empty. And now we're going to start putting a point in space, and each one of these points is a domain name. We're going to put these domain names randomly throughout space, but the points are uniformly distributed, right? So they're all the same distance from each other. And once we've placed all of those points, for each point, we calculate the pairwise similarity with every other point in the space. And based off of that similarity, we put a vector pulling that point closer or further away to the other points based on its similarity. Oh, here it is. Okay. So this is a visualization of just that. Oops. Wow, it's not working. Yeah, Murphy's Law, right? Okay, that's unfortunate. But what you should end up seeing is the clustering of these domain names into distinct clusters like this. Okay, we'll just have to skip this. So going back to the key threshold in this algorithm is, how do we define the similarity threshold when we apply our hierarchical agglomerative clustering algorithm? So the next two plots are actually going to look at the effect of changing that similarity threshold in the development of the clusters in the domains that we detect. So here on the x-axis, you can see us decreasing the minimum similarity threshold from 99% to the low 70s. And initially there's a linear relationship, and then it kind of goes exponential, and then it plateaus back out to some kind of linear relationship. And this actually isn't that unexpected, because if you remember before in the CDF plots where I was showing traffic similarities day pre and post, that similarity was lower in that 70s range. And so what we're seeing is those domains being folded into the mix here, and once we pass that lower threshold, the number of domains plateaus back out. Likewise, you can measure the number of distinct clusters, and we see a similar trend where there's a finite or a constant number of distinct clusters as we decrease initially from 99 to the mid-80s. We hit that magical range of days pre and post, the number of clusters increase and then suddenly folds back down as we decrease that similarity threshold, and so on. I'll skip this in terms of time. So now that we have an understanding of how to detect malware and then put it into some kind of meaningful context, the big thing we wanted to do was take this approach and apply it into an entire day's worth of NXD traffic from a ComNet TVCC perspective. And so this figure is what I'll end on, and this is a reflection of the actual detected malware associated domains that we discovered. Each point on this plot is actually a distinct cluster. The number of domains is reflected in that cluster on the x-axis, and the number of distinct /24s requesting the domains in a cluster is on the y-axis. So this kind of gives us a couple of interesting insights. A, unfortunately, there are a lot of points on this graph, right? So there's a lot of bad malware out there. But B, it also gives us some ideas and insights into how different pieces of malware are using DGA algorithms. Some are very heavy, right? They're generating 1,000 domains a day. Others are very, quiet and chatty and maybe only doing a couple. But we can also see, kind of as a proxy, the invasiveness of that piece of malware out there as a global infection through the means of how many distinct /24s do we see that piece of malware coming from. So this kind of opens up a lot of future work where we'd like to take and study these domains longitudinally, or these clusters longitudinally, to see how the malware is evolving with time. So I think in time, we basically, yeah. With that, I'll end. Any questions? Yes.
Arnoldo Mueller from C Machines. Very interesting stuff. I was wondering about the dimensionality of the data. How big are these sets that you are comparing with the Jacquard coefficient?
So after we've applied some filtering based off a minimum number of requests that these domains have to receive, it's in the order of a couple 100,000.
Okay, okay. But is it sparse or is it dense?
It's pretty sparse, to be honest.
Okay.
Yeah.
Did you try any other distance functions?
So we
besides-
looked at cosine similarity, but the resulting clusters didn't have the same effect. We found that Jacquards off the distinct /24s to work a little bit better.
Okay, thanks.
Any other questions?
Hi, Sean Lloyd from Nominet. The pieces of malware that seem to create fewer domains, from your data set, can you tell whether they're just creating the same number but spread over more TLDs?
So from our data set, we cannot tell that. We can only see the domains that they're putting in our TLDs.
You have 4 TLDs that you're observing though, and you don't see any change in the distribution over those 4 between those different malware families?
Well, certain ones are prevalent to common net for the most part, right? But we haven't looked at longitudinal studies to see if it's changed over time.
Thank you.
Yeah.
Any other questions? One more right there.
Do you share this data with anyone?
We are in the process of still finalizing this, and I think that might be something that we'll talk about and look in the future.
Chris Baker from Dyn. I was wondering if you'd used similar, I guess, pattern recognition to do malvertising identification and things of that nature.
I'm sorry, I didn't hear the malvertising.
Yeah, so a very similar domain generation algorithm. Just you wouldn't get an NX domain from it. They usually come back clean.
Right.
But just either through name analysis or something similar.
No, we haven't. But one of our future works is to take these detected clusters and use that as a bootstrap to find the active domain associated with it.
Not a question, but comment, if I may. I guess, Mehmet, Microsoft, the data analysis that you're making, and if there is any way that you can provide almost live, maybe with slight delay, data for analysis, if you can create a platform where you can share that, I think it would be very useful for many people in general to fight with the botnets. And I see. Any other questions here?
Yeah, I've got one. Your graphs showed that you had a lead time against the event and then a tail.
Right.
But you drew the graphs after the end, right? There isn't a predictive quality here in the slope of the line. You don't get 3 days notice there's an attack coming.
Right. It's very, for at least these domain generation algorithms, it's a very finite window of what you can see, right? Other pieces of malware don't use DGA, in which you're going to see a very constant association with those NX domains.
Okay.
Can I borrow your projector for a second? Absolutely.
I do. This is a comment. Hello. Oh, there we go. Okay. We still run the configure sinkhole, so all of the domain names that are registered to the configure name servers end up pointing into HTTP servers that we see that we wrote code. So anyone who can look at the type of data that was described in this presentation, this channel is free. We do not charge either for the DNS or HTTP real-time traffic. And we do have a remote access facility now. You don't have to co-locate with us in order to get our data. So contact me if you can help in any way. That go for you guys too.
He didn't pay me to ask this question, by the way. Any other questions from the crowd? All right, thank you so much. Very interesting presentation. Very interesting. All right, so our pretty much dynamic day continues with 2 more Dyn presentations and 1 presentation with 2 presenters, Dave Knight and Joao.
The
I change. Where is it on how do you start the 69? Yeah, it does. Could this space it?
Thank you, Sebastian. Okay, so this is talk about findings on measurements of how we are going to provision the name servers that will be running in the system that Joe talked about earlier today. Even the idea is that we'll send boxes out into the field, so it's quite delicate to make sure that we dimension those boxes appropriately to deliver the service we want them, because once they are on the other side of the world, it's going to be hard to change anything about them. So we went ahead and did some measurements. There are many things that we want to get from these boxes. Number one, above all of the other considerations, is to have flexible provisioning. We want to have several different services running on them, even if they are DNS services. And we want to be able to take down and move things between machines without having to reinstall anything, because that's always a risky operation and you have caused downtime. So that's the foremost consideration. But then you have a fixed size box, right? You have a certain amount of RAM and CPU on that. I need to know how to make the best use of that. You also want to isolate different components so that if there is an issue with in particular implementation of software, Joe didn't mention it today, but one of the things we have been hearing is that different people want to run different DNS software. So building that flexibility to have someone come up to us and say, I want to run my zone in your platform, but I want to use NSD because I like it better than whatever else, then accommodating that would be nice. But you want to run those things separately and don't have them screw each other up. So for all these things, we want the benefits of virtual machines. But as has been reported in the past, DNS servers and VMs really don't seem to be going well together in terms of performance. There are clear bottlenecks in access to the network interface cards. The supervisor typically handles all of the input-output through one thread, and everyone else has to read from that, so that's a real bottleneck. It wasn't really meant, apparently, for this sort of network usage that DNS servers make of. On top of that, traditional VMs, each of them runs their own copy of the operating system, and that's a lot of RAM that you can burn for little gain, right? So there must be better things out there. With time, things have been getting better. VMs can now use, if you buy the appropriate hardware, this single root input-output virtualization technique, for which you need support in the hardware and in the OS. And it does make things a lot better, as long as you make sure that you have the cards that support it. We almost goofed it because one of the vendors did, I'll make this device better for you, I'll give you this upgrade, and then turned out that the NIC that came on board didn't support this feature, and that was kind of almost an oops moment. And then there is this other thing that's catching on quite nicely, which is Linux containers, which, as Dave describes, it's basically chroot on steroids. Has advantages that it doesn't run entire copies of the operating system, so it conserves RAM, which is a hard consideration for us. So what are we about to go out and measure to find out how things run? We picked the three most interesting or popular authoritative server implementations out there right now. Not 145, NSD 403, and Bind 995. Running on Ubuntu, we tried 2 different versions. And then we started doing combinations of VMs with and without technologies and containers, both with constrained uses of CPUs or not. So I'll now switch to Dave. Oh, well, one more thing. It's a bit tricky to measure DNS servers. Apparently, you should think that this is a trivial exercise. You just have a server, you throw queries at it, you read what the number comes on the other side. In practice, it never is quite like that. What you do, how you ask the questions has an influence on what you get back. How you run the server has an influence. How your network setup is makes a difference. To do this, we use the DNS perf, but we validated the findings against running multiple queries of multiple instances of query perf, and we weren't happy until we kind of obtained the same results from both sets of measurements. So it's definitely delicate, I should say. We were content when things were within a few percent of each other, independently of how we measure them. However, as you will see, there is still a couple of points of data that will need further exploration. So now off to Dave.
Thank you. So we use Supermicros for this. I have a rack in the basement of my house, which has a stack of boxes in it, and that's where we did this testing. So this diagram shows all of the machines that we used for all of the tests that we did. So this controller box at the top, its job is just, that's where we run the testing from. It can SSH as route to the other boxes to start scripts and start the queries. And the queries are done over a direct cable between the query source and the name server box, so it's not hitting the switch at all. The traffic over the switch is just the control traffic. So the control box, it doesn't really matter what operating system on that, it's an older version of Ubuntu. Both of the query source and the name servers were running latest everything, with the exception of Docker. Docker is the container management tool that we use, and it's in ridiculously active development right now. So we pinned that to an older version that we were sure actually did the things that we need, because it seems to change from day to day what it can actually do. So the way that we ran the tests, everything was scripted. So this controller box also had an install server Pixie boot thing. So between each test, we would wipe and reinstall the machines just to ensure that we hadn't left any stupid things in the configuration between different testing. And then for each test, that would be fully scripted up. So in preparation, the controller box would reach out to the name server, and it would pull all of it would pull bind and not and things from FTP sites, build them in place on the box, create containers, all fully automated, so that we tried to remove all possibility of human error in what we were doing. And then during the actual testing, the script running the test connects to the name server box, lights up a container with the name server in it, connects to the query box, starts a 60-second blast of DNS perf towards that, and then it tears it down again, records the results, and then moves on and starts the next test. Because we were testing 3 implementations, and for each implementation, we ran with 1 through 8 workers for the name server. And then when we were testing in containers, we also tested CPU pinning. So we picked sort of a set of different pinnings to try and exercise the cores in the CPU, putting the 2 same hyperthreads that were on a core together, and then having them on different cores to see what the effects of that were for the name server. For VMs, so yeah, as Jacques explained, we assume it's the received wisdom is we don't run high performance DNS servers in a VM. But new technologies like SRIOV challenge that somewhat. I'd never heard it before until somebody mentioned it at Dyn a few weeks ago, so we decided to check that out. So what we did there, we created a virtual machine with Ubuntu 14.04 in there, and we're able to use the exact same image between the tests. It's outside of the virtual machine is where you configure how it attaches to the network. So, we could light it up with a bridge and the plain old fashioned, and we can also light it up with SRIOV. So when we did that with a bridge, inside the VM, we create 2 Ethernet interfaces. One which is like on the physical box setup is where the control information comes in. The other one is where the DNS queries are done. Those virtual interfaces are mapped to bridges on the physical box, and then those bridges are mapped onto the physical interfaces of the box. So the virtual interfaces inside the VM can talk on the respective LANs, and so it behaves otherwise, as if it was the physical machine. We bind the name server to a dummy interface inside the VM where we put the service address, which is what we would expect to advertise in BGP in a real production setup. And we do static routing to point the traffic in towards that. When we run this with SRIOV, there's no bridge. SRIOV essentially creates virtual NICs inside the NIC hardware. On the NIC that we're using, I think we can have up to 7 virtual NICs per port, and the NIC has 2 ports. For this testing, we just configured it to have 1 virtual NIC per port. And in the configuration of the VM, we plumb that in, and so now ETH0 and ETH1 inside the VM are attached to a virtual function on the physical ETH0 and ETH1. So this was these are the numbers we got for bridge versus SRIOV. So this thick line at the bottom is the performance for bind, NOT, and NSD with a bridge. It maxed out, and for all the server was never really being exercised. The network I/O using the bridge killed it at about 10 to 15,000 queries a second. With SRIOV, bind was able to do, I guess, around 80,000 queries a second, and NSD and NOT around 300,000. And what we found is that that's about half of what we would see just running the name server natively on the box without any VM. So it's still not as good as native performance, but it's significantly better than what can be done with a bridge. And so I guess that's enough of the VMs. I'll move on to containers. So we use this thing Docker. Docker is a tool to manage Linux containers. It started out using an existing management tool called LXC. And in a very recent version, they have implemented their own lib container, which can drive kernel namespaces directly. So they no longer use LXC, which was one of the reasons why we continued to use the older version, because in order to do the CPU pinning things that we were doing, that used LXC options, which they have not yet implemented in their lib container. And so the new version for us works a bit worse than the old one did, but apparently that's coming soon. So Docker takes the Linux container and adds a bunch of technologies to it to make it more useful. So inside a Docker container, you have a union file system. So you can start with a base Ubuntu image in your container, and then as you add things to that, you install a name server. It's creating new layers. So it's then very easy to sort of take diffs between containers and push small changes out to affect changes at the edge. And they're very easy to start and stop. There's no, unlike a virtual machine, you're not booting anything. You're just essentially starting an application that's just wrapped in the kernel by the container. And it's very easy to affect changes to containers across the network. So Docker's default behavior is when you light up a container, it creates a virtual Ethernet interface inside the container, and it gives that a dynamic private address. The Docker container is attached to a bridge, which I have neglected to put in this picture. Sorry about that. So there's a bridge outside of the containers, and the container's attached to that. The bridge is numbered with a /16, and each container gets, a incrementing final octet that hasn't been used previously. And the way that you get traffic in and out of that, so in order to put a publicly routable service address in front of a contained name server, it uses IP tables so we would bind that to a dummy interface outside of the container, and then it uses IP tables to NAT specific ports into the private address inside the container. We don't like the idea of NAT in front of the name server, particularly because IP tables on Linux, when you do any kind of NAT, it becomes stateful, and you can't make it not stateful. We tried a couple of things. There's the Xtables add-ons, which does let you implement a completely stateless NAT with no connection tracking. But in Ubuntu 14.04, when you get the first packet against its raw post table, the kernel panics. So we gave up on that quite quickly. And also the IP Route 2 suite has a traffic control, TC tool, traffic control, which also purports to be able to do stateless NAT, but it was really quite hard and I couldn't make it work. But thinking about it, we don't want any kind of NAT at all. Trying to make a stateless NAT is just, polishing a turd. So Docker wants to create its virtual interface, and it wants to give it its private address, and currently there's no way to override that. But in theory, if we could put the publicly routable service address inside the container, we can just poke a route into the container and we need no NAT and everything ought to work. But Docker itself doesn't let you do that. And we can't run ifconfig inside the container because part of the setup of the container is that it drops the ability for things inside the container to be able to touch these things in the kernel. Now, you can run the container in a privileged mode, which gives you all these capabilities back, but then we've thrown away many of the benefits of the container. But after looking around for a while, I found someone else had made a tool to do something slightly different, but it taught me that you can use the IP tool from the IP Route 2 package can manipulate kernel namespaces. So you can say IP network namespace, the PID of the container, and exec IP again inside the container. And so from outside, as root, you can create interfaces inside the container. So I wrote a wrapper script which, when we light up the container, it inspects it to find out what private address is inside. It then figures out what its namespace is in the kernel and then uses IP to poke into it and create an alias on its Ethernet 0 with the service address. And then we can just do route towards that, and we have no NAT, and we can get packets in and out of the name server, and it's all good. So as Joy mentioned, one of the reasons that we want to use containers is because it will let us define budgets, predictable budgeting for the resources. What we can do with Docker, we can set a memory limit. So if the process is running inside the container exceed that limit, then it will just tear the container down. We can assign a priority to containers, so that's just a weight. So we can weight particular containers more than the other, and we can also do CPU pinning to pin a container to specific hyperthreads, cores, whatever. And I will step aside again and let Joao explain the results.
So hello again. So this is a quick comparison of what we measured when we are pitching containers, as Dave just described, against VMs running SRIOVs. It's kind of interesting to look at this. It's pretty clear that the process model that each of the name servers uses affects the results quite noticeably. The VMs, for instance, here were limited to 4 CPUs. And what's changing at the bottom is the number of worker threads or worker processes that are running. So if you see 1, 2, 3, 4, 8, and well, it should be 16. I guess I got the scale wrong on that one. You'll understand why the graphs look like the way they do, right? So there was the first thing that struck us here is that contrary to instinctive knowledge, for the case of 1 CPU, the VMs actually run a little bit faster, but then they don't scale after that. Whereas containers kind of is more like running on the bare metal, and they do scale with increasing numbers of CPUs. In the case of Bind, which is a multi-threaded program, the software continues to scale its performance up until a certain point, which is the 8. This is run on machines with 4 cores. Each has its own hyperthread thing that Intel puts in there. So it has 8 logical CPUs. That's the correspondent to the number 5. So until you reach that thing, adding new that limit, adding new worker processes keeps increasing the performance of Bind. With the other ones, which are actually not threads, but it's individual fork processes, you reach that limit when it gets to 4, which is the number of machines, or 3, as it may be with the case in NOT. And then it all goes to hell, basically. The processes start competing for the resources, and they don't cooperate well. So far, so good. Trying to see what things look like when you restrict what CPUs can be used by the system. There is general wisdom out there that if you keep a process running on the same CPU between context switches, there's a chance that when the process gets back onto runtime, there might be some relevant stuff left in the cache, and the cache hits really affect performance of services. So let's find out. What we are picturing here basically is the difference between running the process with the process pinned to CPUs versus letting the OS scale things as best as it can. And of course, the OS is not stupid, right? Recent the most recent Linux kernels, for instance, do know about there being advantages of reusing cache contents, and they try to kind of keep processes close to where they were running first, if they can. So the differences in the graphs with the little dots and without the little dots are that in one, the CPU sets that were assigned to the processes were actually in different cores. So there weren't two hyperthreads running on the same core, whereas the ones without the dots had processes that would share the two hyperthreads in the same core. Of course, what this shows basically is that, in fact, for some better than others, hyperthreading is an illusion, right? You're just pretending that you have things that you don't actually have. And of course, just like in the previous thing, bind as a multi-threaded program kind of copes with this better than the independent processes, which don't really cooperate with each other. And that's what it's showing. There's little odd result for not on the bottom line, because it suddenly shoots up. And looked at the tables, the numbers are what they are, but they don't make any sense. So we have to revisit that particular data point. Other than that, you can see the effects. For instance, the bottom line, the bottom blue line, which is bind, you can see if using one CPU and the same CPU and the second CPU on the same core, you lose some performance. Adding the third, which is on the different core, doesn't make you lose anything, doesn't gain you anything either. And then if you add the second CPU, the second hyperthread on the second core as well, then it doesn't work basically. So it's a notice to navigators. Basically, hyperthreads are not what they are purported to be. And then, just for completion's sake, we had two different platforms, some older Xions, Ivy Bridge, and the new ones, Haswell. So there is some mythology about that Haswell is faster, but it scales worse than Ivy Bridge. So we decided, like, well, let's have a look. And those are the two comparisons. Haswell is indeed faster. Every single curve that uses Haswell starts off being faster. In the case of bind, the two lines are parallel, so it's kind of, it really makes uses of the system as best as it can. It's a pity that it's, in all cases, it's also the slowest one, but there you go. And the others, again, have some truth in the fact that Haswell scales less to more CPUs as you add the CPUs than does Ivy Bridge, but it's not really significant. You'd be well off with either of them choices, so that's not a determining factor, really. Thank you, Keith. Okay, so questions for anyone? Come up.
Randy Bush. For the virtual NICs, did you test what happens if you there's contention?
If there is contention within the NIC.
Right, if you're trying to use more than one virtual NIC at the same time.
No, we didn't test that. We, as Dave said, well, you can say it.
Yeah, I mean, we're not finished with this testing. What we've done.
I'm not
so
asking for a refund. It's okay.
Okay. But yeah, just to finish that, we do intend to sort of post something somewhere with a follow-up with results of more tests.
Yeah. Also, because one of the things that we have observed is that the memory usage pattern, which we never talked about. We are only talking about QPSs here. But another important thing is how these name servers scale when you increase the number of zones, right? And there are two factors there. Is how efficient is memory usage to store the zones? And for instance, not 1.4 sucks at its memory usage.
But now you're starting to test the name servers, not the delivery on virtualization.
Right.
So
we have, this is basically, that's how we introduced. We have a set of constraints. We want to find what works best, right? And then there's concurrency, running more than one, because we want to run these things side by side. The whole idea of the containers is that you'll have different customers running on that. And if they interact badly, we need to know that ahead, right?
Given the irregularity, let's say, of the curves in the container space, would you operate in that space?
Not immediately. As Dave mentioned, we went back to 0.81 for Docker because we had problems with the follow-up version. So we'll be following it. They don't break anything. They are just a little bit finicky about their management.
Yeah. Ray Bellis, Nominate. Some years since I did this, and it wasn't in a virtualized environment, but I was finding that with DNS perf tests, that the performance would vary greatly, not just on obviously the CPU pinning of the daemon, but the CPU pinning of the NIC interrupt handler.
Yeah.
Have you looked at how that might work in the virtualized environment? And for example, did you look to see which CPU in the hypervisor was handling the NIC, and whether that was the same CPU as you might have been using for your tests?
No. Someone else, actually somebody in Dyn Labs has been looking into some aspects of that stuff, certainly the interrupt handler and things, but our work is yet to collide. That's one of the things we plan to do in the next couple of weeks, is to bring the work that she's been doing in to test exactly that kind of stuff.
Yeah. But I also found this affected the client side of DNS perf as well. So if you were hitting the limits of what the DNS perf client could do, from memory, I was getting, I think, 80–90% more throughput from DNS perf itself by making sure that there was different affinity on the client side of that test.
Right. The client side, I think we are more confident about that.
Yeah, you're probably
I said we run DNS perf against query perf. Query perf needs several instances to get the rates of queries that you get from DNS perf, but they all maxed out at the same level. Okay. So basically, the client side, I think we basically validated it.
Yeah. Okay. Thanks.
So Warren Kamari, Google. Similar question to Randy's. Did you do all of your testing in one container, or have you tested multiple containers in the same box?
Yeah, that's exactly the next thing that we want to do, is to move on to testing what a real, actually something I didn't mention is that the bulk of these tests were done with a single example.com zone with 10 records in it. And the source of queries was five queries, 3 of things that were actually A records in the zone, 1 which would give an NX domain, and 1 which would give a referral. And that was used in all tests. What we want to move on to next is, let's run 10 containers at once, and let's mix and match things so we can get something that looks like production.
Right. Actually, we had some results from that, but there was a little misunderstanding of what had been saved before a machine wipeout and what had not been saved. So we'll need to repeat some of those tests.
So did you say which virtualization environment you were using, and do you plan to test all the others? Because I've noticed difference in performance between VirtualBox versus KVM versus Zen versus VMware and so forth. And in particular, there's a difference as to whether you tell the virtualization environment to emulate an NE2000 or whether you let it use the purpose-built virtual NIC.
To be honest, to answer the first question, we use KVM, and we used the version that was installed on Ubuntu 14.04. I'm not sure that we're going to explore that a lot further, because we're fairly convinced that we don't want to use VMs. We do want to go down the container path and make that work. So we probably won't do much more work with the VM stuff.
Quick one. You mentioned zone count somewhere, but I didn't see specifics. So can you elaborate?
That's because all these tests were done with a single small zone. The other tests we did with more zones to see how things behave differently, because it's not only about memory usage, it's about the search algorithms that the name servers use when you have more than one. If you have one, it's easy. You don't have to search for anything. Those tests, part of them got wiped out, so they need to be repeated. So they've mentioned we'll be making more of the data here available. I'll probably post a blog post somewhere at Dyn, and there we'll put all the tables. Tables don't look so good in PowerPoint or whatever.
Oh, thanks. And please make sure to test both zone count and zone size. Just like.
Indeed, yes.
Yeah, of course. Thanks.
Martin Levy. So why use VMs? Why use containers? Why do any of this? And I'm going to go push back on Joe's talk earlier about this. The pitch was it makes it easy to do bare metal upgrades remotely, et cetera, et cetera. Sounded good during Joe's talk. This doesn't sound so good. And if we look at what you really want to do with these machines, You only want to do one thing with them. Deliver DNS, grades QPS. Unix is full of tons of stuff, but you could strip something down to nothing and go a completely different route. And the graphs here, I hate to say it, I feel like you're hitting your head against a brick wall. Is there a completely different mindset here that maybe you're proving this isn't the right direction to go?
No, it actually is the right direction to go. Not only does it make the management a lot easier and more versatile, it kind of actually contains, as the word says, certain pieces of software and all their security issues to within a part of the system. The graphs, maybe there were too many. But basically what they are showing is name servers that use the independent process approach scale fairly decent if you're using real CPUs. And then they fall off, basically, and which is kind of what you expect, really. So this was a fact-finding of how far can you stretch things. Does it matter that they fall off? Well, depends how you're intending to use the machines. What we learned from this is if you have 4 CPUs, don't believe anything that's being told. You're being told about hyperthreads. They just smoke and mirrors, really. They don't work. Maybe you can leave some side tasks to them, but don't count on using them for any service. Bind, which is a multi-threaded process, somehow scales better, probably because the threads are a little bit more collaborative. But the problem is you start from a bit lower in the performance. So it's all predictable. It's all quite clear, I would say, if you actually look at the graphs. And the containers, the main issue we have with the containers now is that, for instance, Docker is actually evolving. Its software is evolving very, very quickly. So we need to keep on watching it for a little longer and gain confidence that it is. But it does buy us stuff.
Yeah, one thing I would add to that is I don't think there was a graph that really pointed it out, but the performance of the name server running in a container is generally
twice.
Sorry?
What, twice?
It's what, twice?
Faster.
Than the performance of a name server running a container is not that much different from running on the bare OS. Yeah. You know, in a VM, even with SRIOV, it halves the performance. But in a container, you don't lose much, but you get a lot of benefits from the container. So yes, we want to use containers.
Is it? So it behaves like a split brain thing.
Well,
oh, it says
just
not is multi-threaded, not cooperative processes. Sorry. So it does behave very weirdly then. We should talk, yes.
It's possibly something to follow up afterwards. I was just curious about how much optimization you did with the query generator and whether you tried any other.
So we tried, for instance, I don't know what you mean optimization with the query rate. We tried to make sure that we were actually maximizing the number of servers, the queries that the server could answer. We did try, for instance, different things. We did try varying the ratio of queries that result in data being returned versus NX domains versus things like rejected, whatever the word is. Refused, yes. And that affects things a little bit, but not spectacularly.
There are tuning parameters for the various generators that can affect
the
throughput that you can get. I wondered how much
tuned those.
optimizing.
We also tuned those, like number of outstanding queries, maximum timeout, and that kind of thing. We also looked at those because in the past that has been an issue.
Yeah.
Any other questions for Joao and Dave? All right. Thank you very much, guys, for the presentation. Now we are going to go for a coffee break, but 2 quick reminders. One, we are, I guess, still looking for volunteers that wants to help with the program committee. And if you have not registered, please register. And for the program committee volunteers, please talk to Keith or our chair, Sebastian. Thank you. We have 20 minutes, right?
No. Okay. We're running very well on time, so we're going to give
Let's start our last part of our meeting. Martin, Louis.
These are stack ranked according to how bad they are. More cowbell. There we go, I'm too tall.
This is quite an old bad idea.
Yep, this is a very bad old idea. So I was actually kind of scared about presenting this.
Can you give me a second, Warren?
Sure.
Yeah, thank you. So we have 6 lightning talks, 5 minutes each. We're going to be very, very tight on the time. So there you go. So the first one is Warren Kumari with bad idea number 17. Go.
So yeah, this might be a really bad idea. Keys, no rocks, pointy sticks, etc. You can save those for later. A couple of us are planning on writing this up as a draft, and this is not a new idea. People have been talking about it for a while. We're finally just going to actually document it. So one of the good things about DNSSEC is it doesn't actually matter where you get the data from. You know, you can get it off the back of a bathroom stall on the graffiti, write it down. As long as you validate it, it really doesn't matter where it comes from. Presumably everybody here knows how a recursive resolver works. It starts up, it's got an empty cache, and then for every query in an uncached TLD, it has to go off and poke the root, download information, blah, blah, blah. If you have a look, very shortly after a recursive starts up, it generally has all of the TLDs in its cache because spam and various other things make you reach places all over the place. So what we're proposing is iterative or recursive resolvers, whatever you want to call them, should simply slave the root, and they transfer the zone using whatever. Could be BitTorrent, could be AXFR, could be FTP, doesn't really matter. They get the data somehow. They must validate it, and obviously not use it if it doesn't validate. And then if they're unable to transfer it, just fall back to using the current legacy system. Once they're slaving the root, obviously any queries that come in for stuff in the root, they will have that answer immediately. I'm trying to go through this quickly so people can shout. One of the big wins from this is there's currently a political nuisance here. You know, there are 13 letters, 12 organizations, most of them are in the US. How come country X doesn't have a root server operator? Apparently this is something that's important to people. Don't entirely get it, but anyway. There is a small latency and stability win. Every now and then entire countries fall off the internet, and then they can't resolve things even within their own country if they happen to have servers, because they don't have a root anymore. There's one less piece of infrastructure to go boom. Obviously there's less junk queries hitting the root, because, well, there's less stuff hitting the root. Some of the scary things, there's no longer a central place to monitor stuff, like there is no more diddle data. This is also potentially a win because there's no central place to monitor stuff. You also lose the ability to make fast changes. So if somehow you accidentally screw up this zone, you can no longer just send it off to a few people unless you manage to notify it to 180,000 recursive resolvers, which obviously is not practical. Questions, tomatoes? Yep.
How about key rollovers?
Key rollovers, I believe, are exactly the same. A new key gets stuck in the new root zone. You validate it using the old one like you normally would. Same as 5011, I think, but I haven't really thought that through, so let me not make shit up on the fly. Jim.
Jim Reeds. What are you going to do about these slave name servers if they fail to pick up a change to the real root because, say, for example, a delegation's been added or changed and they're just too slow to pick up at the zone refresh rate?
So currently the negative cache TTL was something silly like 2 days, I believe. The refresh time is substantially less. So if a new TLD is added, a lot of things don't pick it up anyway because they've got it negatively cached, or at least some things might. It does mean that you can only add new entries to the root every however often your refreshes, plus a little bit because some people won't actually do the refresh. So yeah, it becomes slightly less dynamic. This might be a win. It depends on if you think adding a bunch of new TLDs is a good thing or not.
Largely managed node. One of the consequences of must validate is that you still have to bootstrap this with a trust anchor of some kind. Yeah.
Yep, you still need to know where to transfer this from. It could be the roots, it could be BitTorrent, it could be whatever, new infrastructure. But yeah, you do still need an original trust anchor to start from. Wow, either people are shocked or they're not as grumpy as I was expecting. Oh.
Yeah, microphone.
How about right now we have secure systems obviously that manage the root servers, right? Root operators. How about like somebody actually hijacking and just making sure those, you know, they serve a different root zone?
Well, then they won't be,
and it's in the
validate.
cache.
Then it won't validate. That's the whole thing of you have to validate the zone when you download it. So
Okay.
if somebody stands up a fake zone, it's the same as trying to stand up a fake root server currently. You'll get the data, it will be bad, you won't use it unless
Okay.
I misunderstand it.
Okay.
Thank you.
Oh dear.
So you do rely on all the sub-TLD, all the TLDs actually being signed and having a DS. Because if you have a TLD without DS, you have unsigned. Yeah, but you're not. If you sign the, are we talking about a TSIG-like signature, or are we talking about validating the DNSSEC records? The DNS records at the root are not signed. The delegations are not signed. And if there is no DS, then if you follow the delegation, you end up in Zilch, and that can be hijacked.
Just as you, I think.
Sorry, you can take the discussion
up. About that.
Yeah, yeah. Thank you very much, Warren. Paul?
Sorry. Hello? I have one more question. Warren, here, over here at the back. One more question. So, if it's an authoritative name server and it slaves the root, then it can never hand out an AD bit for that root, can it? Being a resolver at the same time, I mean. Okay.
Okay, Paul, 5.
So let me talk about newly observed domains. What you're seeing on this screen is the timestamp and the domain name of, and you're seeing me play with Windows too, the timestamp and the new domain name of a newly observed domain in the passive DNS system that we run. So we collect about 1 terabyte per day of cache miss traffic. My oldest sensor operator in the room would be Randy Bush. Thank you very much, Randy. We share this with various people for various reasons. Commercial people pay money, academic people don't, and so on. I took this with me when I left ISC last year. So by the time we've post-processed all of this stuff, removed all the duplicates, removed all the DNS tunnels, a lot of the PTR records, a lot of the pure junk, we are left with around 10,000 messages per second that are worth something to us when we put them into the database. At previous OARC meetings, I've given you a demonstration of the passive DNS database, so I won't be doing that today. This is something that came after that. So we take this 10,000 message per second flow and run it through a Bloom filter. So we keep about the last 10 days of name existence. And it's not exactly a Bloom filter because you can delete from it, but the point is we reduce that 10,000 to about 50, which are newly observed or newly active. They're active for the first time in the last 10 days. And at 50 messages per second, it's a very good flow if you're doing brand enforcement because you can actually run Soundex and other fuzzy text matching systems at that speed. Also, 50 messages per second is a low enough volume that you don't mind having it delivered to you over the wide area network. That's one of the other things we did recently. I described this earlier. We can now deliver real-time products over TCP flows rather than making you connect to our switch in a data center. But anyway, the last 10 days is still not quite interesting enough, and 50 per second is faster than what you're seeing. In fact, it's so fast that I can't read it. So we came up with something slower. We looked into our database that goes back to June of 2010 for every message in that 50 message per second flow. And if it's a name we've never seen, then in addition to putting it into the database, it goes into a real-time channel. That's the channel you're looking at. These are names we've never seen. I believe our coverage is somewhere around 50%, give or take 40%. A lot of these, if you run whois on them, you'll see that we just missed it. Nomnomspicy.com, for example, that has to have existed before today, but somebody do a whois on it for me and let me know if it's a good or bad. A lot of them have today's date when I check them. A lot of them don't. These are authoritative domain names. These are seen in cache misses.
So that one's today.
Okay, so nomnomspicy.com was a win for us. So anyway, if I'm right that I'm, seeing about half the names on the internet as they are created, and I'm not yet seeing the rest, that helps you understand why I'm coming to Europe for 3 weeks in June to request more universities to trade data with me, because we need better coverage. But also, if I'm right, you're looking at the pulse of the internet DNS. This is within an order of magnitude of the speed with which new names enter the DNS. And that's kind of fun. I keep this running all the time now on my laptop, and it's very distracting. And we have not stripped any labels. These are the new name. This is the highest order newness that we could find. So it may be that we stripped the label off the Q name because the parent of the Q name was new to us. So these are the actual new names. Actually, we ship both, but I'm only printing one in this tool. So this informs my rather dark opinion of new domain names. I said that they were mostly crap, and I mean that they're this. And most of them, especially those .tk names, are going to be subject to rapid takedown when they are used in spam. And so if you've heard me say that the older a domain gets, the less likely it is to be subject for takedown, I have the data. Questions? Joe.
So I forget how you collect these things, but are some of these typos potentially, or are you looking actually at responses?
These are actual RR sets that have one or more records in them. I didn't print the query type that gave rise to it, but this is real data. These are not typos. I was thinking we would add NX domains as a similar channel because that would also be fun to look at. Any other questions? Thank you.
Thank you, Paul. Next on the list, Mehmet.
So I wasn't actually planning to make a presentation, but I had it handy. So I'm sure there are so many people here that works with TLDs all the time in different venues, and presentation includes actually some different things that are not related with CCTLDs, but my focus is going to be just the CCTLD portion. As you guys know, there are a lot of people in different organizations that uses Microsoft products, and there might be some vulnerabilities that those machines are infected with. So we have received about 2 years ago a big complaint about some sort of vulnerability affecting a database that fed the DNS servers, and the team the TWC team in Microsoft have developed this security scan service, which is completely free. It's very simple to sign up for. I'm going to skip these parts real quick. Just common email addresses at Microsoft in case if you have questions. One is dns@microsoft.com, any kind of general DNS questions. The other one is DNSSEC if you have DNSSEC specific questions. And for the scan services, cctldirectsec@microsoft.com. We will be around here anyway, so I'm just going to go for the security part of it. You can go to this URL, aka.ms/cctldscan. If you're running a ccTLD, or if you know anyone that's running a ccTLD and that's interested in this service, all they need to do is simply email to this address, and we will get in a very simple legal agreement, 2-page legal agreement, and do the scan and provide them feedback. We don't disclose the ones that we do the scan with, but there are some numbers that I can vaguely give so that you guys understand. We have 21 people that has contacted us since the ICANN meeting in Singapore. And so 7 of them has already completed their scans, and we were able to find 138 bug or vulnerability, I should say, that we consider as high impact. Those could be some configuration in the database permissions. We consider them as potential problems because some simple user can jump with different access rights and delete everything. Those kind of things we were able to detect and help them. Again, this is free service, and we just want to help. The other thing is we've been very active in the community. We want to learn. There are so many things. There are so many advanced things this community is sharing, and we are here to learn. But also we want feedback. We want to learn from you about our products. We are, it's really that we have a lot of clients in the world. Once I get more involved with Microsoft, I keep understanding that globally we have so many clients. We want to make a better software for those that are going to continue to use us. So what can we do? You can talk to us in these places. That's really it. My goal is to let people know about the ccTLD scan service, and if anyone is interested, they can come and talk to me in more details about what kind of scans those are.
Any question for Mehmet?
Thank you.
Okay, thank you. Matthew, go up.
All right, so I didn't do up slides for this because I don't plan to be up here staring at that light any longer than I have to. I've been kicking around a project idea for a while now, and I kind of wanted to get a feel for whether people would find this useful or not. The idea I had was shortly after Stefan put his Looking Glass software out, of doing something like building a standard VM distributed from a central location, managed from Puppet, Chef, whatever, that people could download, stick in their network to provide a Looking Glass to the internet for the DNS without having to do any work and manage it themselves. So to run, somebody's existing Looking Glass software, like Stefan's, maybe more than one, to provide multiple interfaces if people prefer working with different types of Looking Glasses. All managed centrally, and pretty simple, pretty easy to manage. So rather than waiting for questions, I actually have questions for the group. If something like this existed, who would actually run it in their network? Anybody? Yep. All right. All right. So it's just a rough idea right now, not a lot of details, but yeah, questions?
Hi, Jared Mott. So I actually have a list of all the DNS servers on the internet, and I don't know if everybody remembers, but about, I don't know, maybe 6 months ago or something like that, there was a whole bunch of high-value domain names, including like fidelity.com and ups.com, that had some extra data kind of inserted in there that caused the delegations to not quite work correctly. And I actually had somebody from CDN come to me and said, hey, you've just done this big thing. How hard would it be for you to just ask them all and figure out who has the correct answers and to kind of give a sense so we can communicate back to our customers? So I actually have some tools around surveying several million DNS servers at once from one point. And I would be happy to share the tools as well as the list of all of the DNS servers with people who, the ones that actually respond from port 53 as opposed to from some random port and other stuff.
Yeah, I was thinking more of a deliberate looking glass rather than just taking advantage of open recursives. But yeah,
I would rather survey everything and then you know what's wrong.
Just to understand, how is this any different than NLNog's ring?
It has some similarities, but NLNog is a shell you've got access to with some processing limits assigned, right? As I understand, there are some restrictions in there about what you're allowed to do and so forth.
But you can do dig or you can.
It definitely has some similarities. The difference here is that it's explicitly providing a looking glass which would be available to the internet at large, rather than just providing a shell for your network to do stuff from.
Okay. If it is possible, it would be great to see you guys work together because they are already widely deployed.
Yeah.
That would really make things easy. Just a comment.
It's also. Oh, sorry.
Hi, Nat Morris, ESCOM. My point was similar to Mehmet's about getting in touch with Job Snijders at NLNog and try and work with them, and also to look at the RIPE Atlas project.
Yeah.
Because I use that myself to monitor DNS instances, and
yeah,
that team are really accommodating, and they'll be upstairs this week and talk to Daniel Quinn.
Yeah, but again, Atlas is a closed system, right? It's not. Just anybody on the internet can't go to Atlas and stick queries in, which is what you can do with a looking glass. Yeah.
Lars Lehmann from NetNode. I would just like to point out the significant difference between having a centralized system and having looking glasses, because looking glasses can look from different angles at any cost systems and give the different properties seen from different views. So I would find that very useful, even though we are probably not the best point to put one, but I would definitely have a lot of use for such a system. And you're very right. There's also a significant difference between the Atlas system and your system, which is that the Atlas system gives you a subset of data, whereas a looking glass will probably give you the full content of the DNS message that you can pick apart yourself if you want to. Thank you.
There is also a big difference in quantity between NLNog ring and Atlas, but in both cases, they may be insufficient for the task. Sometimes the phenomenon we want to see are very local. Last week, I wanted to investigate DNS problem in Algeria, and there is no NLNog machines in Algeria, not even a running Atlas probe. So sometimes when you have a phenomenon that is limited to a specific region, a specific AS, a specific prefix, we simply need thousands, dozens of thousands of probes. That would be, in my opinion, the long-term goal.
Last two questions, please, Martin.
Build a package, not a distribution like you're talking about, because some people like ourselves actually have a lot of machines or VPSs around the globe that we could run this on top of our existing tools, which will give you a wider spread, and it actually completely answers the Algerian question, because in our case we needed Turkey 4 or 5 weeks ago, and we had that, and DNS results were quite interesting from Turkey.
Yeah, I guess for people who are really willing to manage it themselves, I could do something like that. The original idea I was thinking of is that because this involves managing a web server and some sort of CGI or something behind it, and it's for some people it would be simpler just to set it up and forget about it and let somebody else manage it.
Yeah,
but
we could do both. To compare it to NL Ring, which is wonderful in the BGP world, it's actually quite heavy to go run an NL Ring setup. You want something easier than that.
Yeah.
Last question, Randy.
Randy Bush. I find NL Ring pretty light, actually, and pretty stupid. I just put it up and it's gone. What I'm missing is the topology information. You know, hey, I want to have views from A, B, and C in the network topology, not geography. And that becomes interesting.
Yeah, there might be a way to accommodate that. Just by
Well, the
getting those
NL Ring has that problem too.
Yeah.
So I'm just saying, in general, those fielding these kinds of services, for those of us who are trying to diagnose any cast, as Stefan says, etc., topology is what's important.
Yeah, I hadn't thought of that, but there may be a way to address it by getting the hoster to supply some additional information, or possibly.
And in general, I'm not tempted. NL Ring does what I need. And I think, to answer your question, these things tend to be deployed by what I call the clue core, right? The people near the center of the internet who have clue, and they put up ripe atlas anchors, and they peer with the Oregon and Riperus, and they'll put up NL Ring, and they'll do these things. We get a very biased topology, very biased topology. And as someone who plays a little in the network topology space, that's very frustrating. And actually, Atlas is a little less biased because they're teeny and we scatter them like peanuts. But
all right, thanks for your comment. That's all the time you have.
Hello, my name is Patrik Wallström. I work for the Swedish. I'm too tall for this. I work for the Swedish ccTLD.se, and together with AFNIC we have a collaboration about rewriting our old DNS delegation checking tools, DNS check and zone check. And the hardest part with the whole project, I think, is to come up with a new name for a DNS testing tool. We had this name competition within our campus for like 4 months, but finally we decided on the new name. It collides with some sort of ventilation company somewhere, but that we don't care about. And the reasons why we wanted to rewrite DNS check from the thesis point of view is that we wanted to have a new code base to implement new future features, and also have reproducible results, because sometimes when you rerun the test you didn't get the exact same result. AFNIC was also looking out to rewrite their ZoneCheck tool because they had no Ruby coders left that knew the ZoneCheck code base. So both of us decided to implement a new checking tool based on our previous experiences and to create a new reference testing tools for testing DNS delegations. The project was first discussed in I think early 2013 or even late 2012, but other stuff came in the middle of this. For example, .se worked with the pre-delegation testing for ICON, where we used DNS check to test the new GTLDs. So we learned a lot from that experience as well. The majority of the work up until now has been to combine all the requirements from the previous tools and to collect these into a new set of requirements, and from that write new test specifications and all the specifications for the new tools as well. But the code for the new test framework is in place, so that's good. The requirements for version 1.0 is to replicate all the current functionality of DNS check and zone check. So basically all the features that we really need should be in place for the new zone master code. So that includes all the test cases that are currently within the current software. The test specifications are written in the IEEE standard for writing test specifications, but it's loosely based on it, so it does not contain all the stuff that are supposed to be in the IEEE standard. So what we have is the master test plan, which describes the methodology we use to test and how describes how we break this down into test levels. So each individual test is described in a test case. So these are the test levels we have, which combines all the current tests. So each test level contains from like 3 to up till like 11 or 12 tests each. So where we are now is that we have sent out these test specifications to a number of reviewers. They are all written and we have had an internal review. So everything is published on the GitHub website. So I would like to invite you all to take a look at it and read the test specifications. And if you have comments, just comment on GitHub or in the issues or write back to me. We are currently implementing also the test specifications. We don't count on that there would be too much of a change. So if there's a change in the test specifications, there will be a change in the test code as well. So the URLs are these, github.com/.sc/tonmaster, and the specifications is in the other URL here. So any questions about this?
Hi, this is Anand from the RIPE NCC. So we use DNS check extensively. In fact, it's tied in heavily into the reverse DNS provisioning that the RIPE NCC does. So at least for now, we will continue using it. Do you have any plan for DNS check? I mean, how long are you going to keep supporting it with bug fixes or anything? This is just to get an idea of timelines because we do rely upon it heavily.
We haven't decided for how long we are going to maintain the old DNS check code, but it will be for at least a year or two. So, but the continuing development is not that big. That's mostly bug fixes, I think. The new features will be in some master, and that will not be backwards compatible, but it will work in the same fashion. So some master contains a web interface, but what you're using is the backend that does the testing and the reporting. So
okay, thanks.
It will work in the same way. But
Randy Bush, if you want a large black hole to fall into for the CCTLDs I run, I actually test the big time waste is I actually look to see that the name servers are diverse in the RFC 2182 sense. Any hope?
Yeah, we test that currently in the DNS check as well. But what was the question?
They're not in the same data center. They're not on the same backbone.
Yeah. So we will work on that, but please review the test cases because we have one test case that covers the different AS numbers.
No more questions? No? Thank you, Patrick.
Thank you.
Where is Lehman? Lars? Or Jim? Martin? There you go.
I don't think down is the right direction.
Hi, I'm Lars Lehmann from NetNode. I'm just trying to reach out to you with an idea that we just had a few days ago that I managed to discuss with Jim Martin from ISC. And that is that we are within the root server community. We're looking at a common set of statistics that we would like to collect from all the root servers and present so that we can have a tiny little fraction of transparent review of the operations of the root servers. It turns out that you need to collect, of course, that statistics, and you need to share it and also present it. And what we're starting to look at is a common format for exchanging statistics from DNS servers. There are a number of typical statistics sets that are being produced, but they all have different formats, and there are all different expectations of what to receive from name servers, and different players have different expectations. So what we're want to do is to try to start an effort of trying to define a format and also try to define a base set of statistics that name servers can provide. And we're looking for help from software providers, from operators of servers, and also from the end users of these statistics, which are often, at least in the upper layers, the TLD registry operators. So basically, I'm just reaching out to you, say, if you're interested in this issue at all, come and talk to me or to Jim. We're going to create a mailing list for this. We're going to toss a few ideas, but that's really the stage where we are at. And probably you're going to say this has been tried before, but we're still hoping. So that was it.
Any questions?
Comments, questions?
Yes.
Obviously, OARC would very much like to help facilitate that, so let us know how we can assist with that effort.
Okay, great, thank you.
Anyone else? All right.
Okay.
Thank you very much. Fujiwara-san.
Hello, I'm Kazunori Fujiwara from JPRS and University of Tsukuba. and today I will talk about analysis of DITL root data and comparison with the full reservoir data. This is update from my previous analysis. My previous analysis was reported at DNS OARC workshop last year, fall workshop, and there are two updates. I added data from 2006 to 2010 and added some new graphs, and I compared with full reservoir data in 2012. A full reservoir sent 100,000 queries to root within 48 hours, and it may be a typical full reservoir. Dataset and analysis method. First dataset is DNS OARC root dataset, DITL dataset. And I used 8 years data. And analysis method is analysis report method was reported last year, and I wrote C program and which reads pcap files, and it counts number of some kind of queries per IP addresses. And next dataset is University of Tsukuba dataset. Associate researchers and I collected packet captures at one of full reservoirs at University of Tsukuba around January 2011 to August 2012. Data exists at the same timing as DITL 2012. And to analyze the data, I wrote Perl program, which reads pcap files and classifies packets into stub queries, responses, full reservoir to authoritative queries, responses, and classifies destination address into root TLDs, other authoritative servers, parses each section and parses referrals, and counts characteristics. Results. This table is same as last report. And new graphs. I added 4 graphs: number of queries, number of IP addresses, ratio of IP addresses, queries, and port randomization status. And horizontal axis is years from 2006 to 2013. And data are total, update, EDN0, DO, repeat port, UDP sum of, query name root, root DNS key. This graph shows number of queries. Total number of original data difference appeared the total and all data. However, number of queries which support EDN0 and DO bits, DO set are increasing. This graph shows number of IP addresses. And currently, 8 or 9 million IP addresses are observed. And this line and this triangle shows IP addresses which support EDN0 and DO. They are increasing. And this graph shows ratio of addresses and queries. Sorry. How to okay. This line shows this line shows this line shows number of queries which support EDN0 and DO and increasing, and this line shows number of IP addresses, ratio of IP addresses which support EDN0 and DO bit set. They are increasing. And I need to evaluate port randomization status. And I used port numbers, high 8-bit and low 8-bit. And I made a bitmap for all IP addresses. And I used number of changes of port numbers increase and decrease. And I classified 4 categories: unknown, static, limited, and random. And queries from an IP address smaller than 10, I classified number of queries, an IP address and queries smaller than 10 as unknown, and use of high 8-bit smaller than 4, and use of low 8-bit smaller than 4 as static, and use of high 8-bit smaller than 4 or use of low 8-bit smaller than 4 or order change smaller than 4 except static as limited and random others. And this classification is under concern now. This is source port randomization trends. Static use of static port addresses are decreasing now, and limited is also exist, and about both to about 10% of all IP addresses. And use of port randomization is deploying well. And next graph is number of queries sent from each addresses at root 48 hours. This graph is same as last report. And there are 100,000 IP addresses send over this part, send over, thank you. Send 1,000 root queries within 48 hours. And there are three this part, and this number is very high, I think. Without TLD typos, there were 318 TLDs at their NSTTLs, and their NSTTLs were 2 days, and DSTTLs were 1 day at May 2013, and they should be cached within 1 or 2 days. If resolvers work well, they should send only 2 times 318 plus priming plus root DNS key queries at most. However, there are 500,000 IP addresses which send over 1,000 queries within 48 hours. Why? They send both existing name and non-existing name queries. So then I checked some non-IP addresses. My VPS, my home server, and one of JPRS address, one of full resolvers at University of Tsukuba. Then I found that JPRS address sent 22,000 queries to root within 48 hours, and University of one of full resolvers at University of Tsukuba sent 109,000 queries to root within 48 hours. They may be too large, I think. And I pointed, University of Tsukuba full resolver is here, and JPRS address is here. That's too, they send too many queries to root, I think. So I checked status of the full resolver at the university. The full resolver used full resolver software by 9.6, latest version of by 9.6, and the configuration was recursion only without DNSSEC validation, without special configurations. And there are packet captures of the full resolver at the same timing of DITL 2012. Then I checked the packet capture. 72 million packets captured, 400 packets per second. 28 million stub queries, 166 queries per second, and 1 million non-existing TLD queries, typos, and 8,429 unique query source IP addresses observed, and 7 million authoritative queries and answers observed. And they send 118 root queries and answers. And 12,000 responses are code 3 name error, and they may cause from 1 million non-existing TLD queries. And that may be reasonable. And name error cache hit rate may be 99%. It's very high. However, the full resolver sent 105,000 code 0 queries to root. This may be very high. And I checked packet capture. Out of basic delegations, a modern full resolver will start resolving all DNS server names A and quad A simultaneously. If cache is empty, it will send twice as many queries as the number of NSRRs to root. And TLD typos caused 12,000 error responses from root, and most of them were different query names. Some came from small negative cacheable time. And next, the full resolver at the university sent many DNS server name A or quadratic queries to root. They may be cacheable, and they are 87% of root queries. To mitigate attacks, zone TTL is small or why I cannot understand. And to understand this behavior more, I replayed client traffic to some flow resolvers to know that the behavior is true. And input client traffic is 48 hours client query data at University of Tsukuba. Same timing, same query name, query type. And original query source addresses are ignored. Queries are sent from one IP address. And tested full resolvers are bind 9.9.5 without DNSSEC, unbound 1.4.22 without DNSSEC, increase the cache size, specify hard-on referral. And I said I used large cache configuration as message cache size 1 GB, RSS cache size 1 GB, infra cache num hosts 500,000. This is result of replay. All configuration case, root name error is small, 12,000 or 25,000, well cached. Except unbound default configuration case, name error is well cached, I think. However, by 9.9.5 sent 163,000 queries to root, and same as by 9.6 observed data. And enabling DNSSEC validation by 9.9.5 sent 663,000 queries to root. It's very, it's too many, I think. And unbound with large cache configuration sent only 13,000 queries to root, and positive query case only 1,856 queries to root. And two TLD query case, two TLD query and another authoritative query case, unbound sends more queries than bind 9. Summary of replay. It is preliminary result and need more test and detailed analysis. Values changed at every experiment. Both bind 9 and unbound generated too many, around 100,000 queries to root servers within 48 hours. So 100,000 queries to root is real. Queries to root increased 4 times when DNSSEC validation enabled on bind 9. Unbound with default configuration is not good for middle or large scale sites, because unbound with default configuration sent 74,000 positive queries to root, and unbound with large cache sent only 1,800 queries to root. And using unbound may decrease root queries. However, queries to other servers may increase. Conclusion. Port randomization is spreading gradually. However, about 10% of IP addresses are still dangerous. DITL data show that 30,000 IP addresses sent 100,000 or more queries to root DNS servers within 48 hours. A full resolver at University of Tsukuba sent 118,000 100,000 queries within 48 hours to root. As a result of replay experiment, both binary and unbound full resolvers sent around 100,000 queries to root within 48 hours. And binary full resolvers may send many queries to root in servers. Unbound send smaller number of queries to root with large cache configuration. And decreasing queries to root is important, I think. That's all.
Thank you very much. Fujiwara-san, and questions?
Hello, Robert Edmonds, Farside. When you replayed the traffic to the unbound server, was this with the default target fetch policy configuration directive, or did you modify that value at all?
Default configuration case, I don't write very limited config directives. IP addresses and ACLs only.
So set at the default value?
Yes.
Any other questions? Warren?
Thanks. So partly a question, partly a comment. During some of the name collisions, faffiness and excitement, Google did some analysis of the diddle stuff and then compared it to the Google public DNS data and found also very similar, well, some similar stuff to what you have, but also some surprising stuff, like how much the visibility at the root changes because of caching. If you look at the diddle stuff, like .mail is way down the bottom of the list, past 100, but in recursive data, it's sort of item number 1 or item number 2 for unallocated TLDs. Of course, all of this went through our legal and marketing people, and then we published it in an open comment. If people would like to know what it actually meant and not what the lawyers did to it, I'm happy to chat about that.
Any other questions, comments? Randy?
I think this one might be addressed more to Lehman, but in general, I'm interested in a graph where the y-axis is number of queries per some arbitrary unit time, and the x-axis is days since a new GTLD was put in the root.
Homework.
Right? You understand that one? In other words, when they put .squirp in the root, what's the take-up rate of it?
Okay. Any other questions, comments? Well, thank you very much for your hard work, and thank you very much for coming for DNS OARC. Next presenter is someone you have never seen before. The first time, Dwayne. Set you up. Are you gonna? Okay. I just closed it. You want the PowerPoint or PDF? Thank you. Great. Perfect.
Okay, thanks, Mehmet. Whoops. So this is a joint work between myself and Aziz Mohizen, who couldn't make it here today, unfortunately. The subject matter is open resolvers, and if you've been to an OARC meeting before, there's a good chance you've heard me and other people talk about this before. So I hope this is new enough and interesting enough to hold your attention for a while. This is actually also a follow-up to the previous meeting where I was here talking about. I did something similar to what Jared was describing. Sent a lot of queries to all the addresses on the internet, asking them about nytimes.com, and so After that talk, there was a follow-up question asking, how many open resolvers do you see in the ComNet query data? And so I have that today. Just briefly, this is more for people who aren't in the room, but why do we care about this? We care because open resolvers, oops, this is the outline, sorry, I'll skip that. Open resolvers are, of course, used often in DDoS attacks. Their openness makes cache poisoning easier. They're also susceptible to cache snooping, and they're very analogous to mail relays, which, of course, lead to spam and things like that. Of course, when I talk here about open resolvers, I'm talking about the bad kind, not the good kind. I'm talking about the unintentionally open resolvers, the ones that aren't being well monitored and provisioned. So at VeriSign, we've done 2 surveys of the IPv4 address space in the last 6 months or so. First, I'm going to say a little bit. You're going to see this sort of these cartoon pictures throughout the talk. These are sort of the models that we're working from. The first is where we've got. So this box here, the prober and the authoritative name server are our own box. They're just one server doing both functions, and we're sending queries to targets, to every address on the internet. We send them a query. If it's an open resolver, it'll send us a query back to the authoritative name server. We'll answer, and then we'll get that answer back here. So you'll see this Q1, Q2, R1, R2 labeling throughout the talk. So this is one model, and this is the other model where the target actually sends its query onto a forwarder. I don't like the name forwarder because it sort of implies that it's the thing doing the sending, not the receiving. It's maybe a forwardee, but I'm going to use the common terminology and continue to call it a forwarder. So the first survey that I have data for here was one that we did back in October last year. We actually ran this from an Amazon web server host, and this one ran relatively slow. It took 173 hours, something like 5 days. You can see the numbers here for how many queries we sent out. Some 3.6 billion. We received 43 million Q2s. So of those probes we sent, we received a lot of queries back. For those Q2s, they came from 28 million distinct. 43 million queries from 28 million of our probes. Those 28 million probes came from only 277,000 distinct IP addresses. Throughout the talk later, sometimes I refer to those as exit IP addresses. All right. Back on our prober side, we received 34 million R2s from 31 million distinct IP addresses. So these are the sort of numbers that match up with the data that Jared has. This graph shows just the rates at which the queries went out. I just made this for myself just to sort of see that things were working. The red here is the rate of outgoing queries, averaging about 6,000 per second. The green is the Q2s, and the blue is the R2s. And it's mostly flat, but every now and then you'll see these spikes. These are sort of interesting artifacts where every now and then you'll hit a certain target, and they'll query you back like hundreds or thousands of times in response to one query, and you get these interesting spikes. The second survey was more recent. It was actually just a couple of weeks ago, and in this one we ramped it up quite a bit, almost by an order of magnitude. So it took 17 hours. Same number of queries went out. The numbers for the Q2s and the R2s are a lot lower. Well, a little bit lower because, as we'll see, the trend is a downward trend. A lot of these are getting closed now, so that's sort of good news. And here's the chart for that one. So, and since these were different timescales, these are not perfectly comparable. But again, you can see these spikes like this. So just a note about how the data is analyzed and captured. The thing that sends out the probes, all it does is send. It doesn't really try to receive or care what comes back. The packets are captured with TCP dump. After that, then there's this program that writes them out to text files, and those text files get loaded into Hadoop. And then almost all the analysis is done with Hive SQL statements. Okay, so first of all, let's talk about how many of the targets are closed. So in the first survey, 99.1%, and the second survey, 99.2%. That's pretty consistent. So this is how many targets we sent a query to and got nothing in response to them. It just went nowhere. Either there's nobody listening, or you know, the host is off, or whatever. So that means that something like 1% of all the IP addresses will respond to you or forward your query, and that's what these numbers show. Here I'm counting. I may be using a little bit different terminology than other people when I talk about what is an open resolver. At least in this talk, I'm saying it's an open resolver if you got a query to the authoritative name server, or if you got a response from it. If either one of those is true, then I categorize it as an open resolver. Here's our numbers for our two surveys: 33.5 million first and 29 million in the second. And these pretty closely match the numbers from the Open Resolver project. I'm guessing that maybe the difference here is due to the fact that we probably count things differently. I'm not sure that Jared counts these, but anyway, we're pretty close, right? Okay, so among those targets that are open resolvers, a very small percentage of them match this sort of simple model, where the thing that you send the query to is the same address that sends the query back to you. Only 0.6% of the open resolvers behave this way. Almost 80% behave the other way, which is that they forward their query to the forwarder, and then the forwarder is where, you know, we see the Q2 from. So so I was curious, you know, how many of these guys forward to Google Public DNS, and as you can see, it's, well, maybe you can't, it's down here on the bottom, 8.3% in the first survey and 8.9% in the second survey. So that's showing some increasing. So there's actually quite a significant percentage of open resolvers where you'll send them a query, they'll send you a response right away without doing any forwarding on this side. So usually you'll get back a refused query, so that's good. It's, you know, small, it's not going to lead to amplification, but it still is a response. It still is a response that could be used, you know, in a spoofing attack. So that's kind of why I'm counting it as an open resolver. There's a table down here which breaks down all the other R codes. 87% of them turn out to be refused. There's a significant fraction that are returning serve fail, and then sort of a smattering of other ones. And this number actually changed, I would say, quite a bit between our two surveys, so that's probably a good sign that a lot of these things that are out there went from, instead of forwarding, now they're giving us a refused answer. So that's good. Sort of an interesting case related to this is where we probe the target, we get the query to our authoritative name server, but then we get an error back from the target. So it decided to query us, but then decided to return usually a serve fail in this case, and sometimes a refused instead of a serve fail. So not quite sure why that is, but okay. But it's you know, relatively small percentage of things doing that. A higher fraction are doing something even stranger, which is you're getting the query all the way through, getting it to your authoritative name server, but then the response gets blocked or dropped somehow. So almost 5% of the open resolvers are doing that. I guess that's maybe good in terms of, you know, reflection and amplification attacks, but still it shows that there's something functioning there, something working. So in the queries that I'm sending out, actually the responses that are going out from the authoritative name server, they all have the same A record. But in a significant case, like 3.5%, I'm getting back a different A record from the probe. And a lot of times I'm getting back the IP address of the target. So there's quite a few devices out there which if you send them a DNS query, they'll respond with their own IP address very, very helpfully. I think there's a well-known IP camera company that is known to do this, and maybe there's some other ones. Unfortunately, I don't have a breakdown of how many answer with their own IP address versus some other address. The last sort of category I have here is a puzzling case where in my data I didn't see the probe coming back to the authoritative name server, but I got a response and it had the right it had the right data in it. So either they're very good at guessing, or more likely there was a problem in my data collection where I missed logging this part. And I think that holds up because in the first survey that happened 120 times, and in the second survey, which ran much faster, it happened much more often, almost an order of magnitude more often. So that's probably just a logging problem. And so that's the end of categorizing all of the open resolvers. This table, if you can see it down here, adds up to 100%. So I've got a few more slides that are sort of very interesting variations on this, but they're not in those categories. In 2 to 2.5% of the cases, send a probe to a target, and you'll get a response back from a different IP address. So I think it's likely that maybe we're getting the response back from the IP address of the forwarder, although there's no way for me to know for sure. But that's very puzzling. And of course, if you were using, Unix sockets or real applications, you would never get this data back. It wouldn't match and get sent back up, of course. Another interesting case is where I send from a certain port, and my response comes back to me for a different destination port. So if I send from port 1000, I'll get the response back to port 1001, say, or something like that. It doesn't happen often, so I didn't list the percentages here, but it does happen an interesting number of times. And well, yeah, let's skip that. The more common case is where the port changes on the target side. So Jared mentioned this a couple of times. You send a query to port 53, and you get the response back from a random, high port number. This happens almost 50% of the time. Very strange, because you would think if this was a common bug, that means that 50% of the things out there on the internet are written by a single developer or company or something, and they got this wrong, and it's been wrong forever. So I'm hopeful that one day we'll be able to find out exactly what's doing this. It'd be very interesting. And just for fun, a sort of a small number of weird things going on where I think I diagrammed this wrong, but usually when you get a query to your authoritative name server, the RD bit should be set to 0. Sometimes there's RD set to 1 in a query to the authoritative. Sometimes we get back the AA bit in our response from our target. Again, normally you'd expect that to be a non-authoritative answer, but it happens about 1% of the time. Yes? Only on the first response? Oh, interesting. Interesting. I like that. Okay. So, how am I doing on time? Good? Okay. So, spend some time talking about 105 minutes, all right. So, we wanted to look at how the set of open resolvers intersects with the things that query us for .com and .net. It's a little bit hard, actually, at VeriSign to get data for all of the all of the common net sites. There's a lot of them, and so this is just done on a subset of them. This is the data from 4 of our big sites, which are located in Amsterdam, Washington D.C., New York, and San Francisco. And you can see the the letters for the GTLD servers.net that they correspond to. So just keep in mind that this is kind of a sampled subset. So the first question is, what percent of the Open Resolver exit IPs appear in the ComNet query data? And this table kind of details that. And for each of the sites, it's pretty consistent. We see about 65%. This is from the October survey, by the way. About 65% of those Open Resolver exit addresses, so that's from the set of like 270,000. 65% of those show up in the ComNet queries. So the converse of that is that about 5% of all the ComNet IP addresses are in the Open Resolver set. And those 5% are responsible for about 50% of all the queries coming to .com and .net, right? So these are not like standalone devices just forwarding your Open Resolver probes. These are normal real resolvers that happen to have paths to them that allow them to allow anyone to send queries through them. Did I explain that sufficiently? No? Jared gets it. So, so I'll pick on Warren a little bit. So, Google, so almost 10% of the Open Resolvers forward to Google, right? And so that would certainly contribute to this, and the other large public Open Resolvers would be the same. But even if you had a organization that isn't offering a public DNS service, it's still possible that some device in somebody's home will accept your query and then forward it to the official resolver for that ISP or whatever, and then it show up as that ISP's address in our data. So if anyone is ever considering suggesting that you could fix Open Resolvers by just blocking the IP addresses of the Open Resolver address, blocking their addresses in the .com and .net, that would obviously not work. You'd be cutting off half of the queries that we get. This is just the same data shown over the 6-day period of the first survey, just to sort of show that it's relatively consistent over time. And this is for the other column showing again 5 to 6% of the ComNet queries appear in the Open Resolver set, and again 50% of those IP addresses, they're responsible for some 50% of the traffic that we get. For the more recent survey, this one was less than a 24-hour period, so there's just this table here. These numbers are similar, although they are decreasing a little bit. Instead of 65% here, now we're down in the 60% range. Instead of 5.1, we're at 4.8, say. But they're pretty similar. So just wanted to end with a few slides on the geographic distribution of some Open Resolvers, and it's actually not too surprising. It's about what you'd expect. Almost all the countries are represented. Tens of thousands of cities are represented. Numerous organizations and ISPs and networks. All these distributions are standard heavy-tailed internet-type distributions. This map shows the count of Open Resolvers that map back to individual countries, and as you might expect, it sort of corresponds to population, right? So China is big here, United States is big here, Russia is big here, and so on. This one is maybe a little bit more interesting because this shows sort of the ratio of it shows how many Open Resolvers do you have compared to how many internet users do you have in your country. And so if you're towards the dark green here, it means that you've got a higher number of Open Resolvers compared to users, whereas the lighter countries have relatively few Open Resolvers compared to users. So you might think of these as maybe Open Resolver importers and exporters, and they're shifting their their traffic from one country to another for some reason. This graph shows just sort of highlighting a few organizations that we picked out from the data to show, how many Open Resolver targets are forwarding through their exit IP addresses. So obviously, again, Google shows up here at ranking high. Whoops, I think I skipped one there. The same organizations, but instead of counts of resolver IP addresses, this is how many resolver IP addresses per forwarder IP addresses. And then lastly, this is a log scale graph of showing how many forwarders are used per each organization. So takeaway points, there's still many millions of these guys out there on the internet. The trend is decreasing. If you're interested, please visit the Open Resolver project page, and you can see this nice graph that's showing it's been tailing off nicely over the last 6 months or so. So I think that's very good. I think that's I'm very hopeful about that. Most of these Open Resolvers, again, they forward to somewhere else. They forward to an ISP name server or something like that. About half, for some reason, respond from the wrong port. Very puzzling. And again, these what I call the exit addresses are strongly linked to the addresses that we see in the ComNet query data. So that's the end of the presentation. Do we have time for questions?
Questions? Yeah, any questions? You're going to take
Ray Burns, Nominate.
Hey, Ray's awake. Good.
Yeah. Hey, Dwayne. Did you look at any cases where you got multiple responses for a single query?
So I don't, unfortunately, I didn't include any data on that. I mean, I know that happens quite a lot. Yeah. It probably happens. In previous surveys I looked at it, and there were some cases that were so bad it made me think that there were things out there intentionally set up by the bad guys to sort of amplify, their activities. They send one query to somebody, and it sends them back like 1,000 responses.
Yeah. Well, the reason I asked is this thing about getting replies back from the wrong IP address is quite similar to the behavior of the Great Firewall of China, where in certain circumstances, if you're sending queries into Chinese IP space, if it's the wrong query name, you might get a spoofed reply back from the Great Firewall, and then get a real reply back from the address you were actually trying to talk to in the first place.
Yeah, that would be interesting. I didn't look at that, unfortunately. Yeah.
Lars Lehmann, NetNode. About responding from the wrong port. There is a recommendation about port randomization, isn't there? I think that a couple of software guys somewhere actually took that literally.
Got their destined source mixed up in their code, maybe?
No, they ignore the fact of that. When they send out the packet, they randomize the port. So that could be. And that going for the numbers, I would guess, and this is a wild guess, that a good number of these forwarding open resolvers are home CPEs, they are 3G dongles, they are telephones and stuff. Could they be sharing the same broken IP stack, possibly the smaller devices?
Yeah, absolutely. Yeah.
Thanks.
So, I'm asking a question for Eric Zegast, who's not here with us. He says, the report seems to only cover IPv4. How can we best measure IPv6 open resolvers, given that we can't scan the whole address space? And it seems to him that the authoritative servers for GTLD and root would have a great set of IPv6 source addresses that could later be probed for openness. And he wonders if the people in this room might be interested in supporting a similar survey of V6 addresses based in part on the V6-based query data from those servers.
Yeah, that's a good question. So I guess I have a few answers. So yeah, obviously, no one's probably going to scan the whole space, but I've been told that there are a number of techniques for finding out where addresses actually exist in IPv6 space. I haven't tried those myself, but that's one option. I should also mention that we have a tool at VeriSign that's like a self-serve open resolver scan. So you can, if you have some v6 space that you would like to scan, you can go there and enter it. As long as it's not too large, we will send queries to it. As for the last one, I'm a little bit skeptical about using the data from the .com and the root because, again, those queries would be the forwarder's IP addresses and not the target's IP addresses for the most part. So I'm not sure that would work.
Hi, Dwayne.
Randy.
Kelvin has a good paper on how to scan.
Okay. What year was it? Recent or a couple years ago? Okay.
Hi, Dwayne. Jeff Schmidt. Can you go back to those two early line plots, please? There were the rates. Yeah, those. So the x-axis there is time. Did you go through the IP space sequentially?
No. So what I did is in the code I have these these arrays of tables. So I go through. Sequentially, it's all the same last octet,
Mhm.
and then after that, it's all the same second octet, and so on. So it's kind of reversed. It's random, and it's different from survey to survey. So this one was in a different order than this one, and I excluded .0 and .255.
What reason I asked is what stuck out to me here is the remarkable level of the green and the blue lines there, that meaning that the hits are evenly distributed across whatever order you went through things over time.
Right. And there is some waviness here, which appears to be some diurnal stuff, maybe as people turn their devices on or off or something like that. But yeah, for the most part,
It's remarkably level.
It didn't seem to depend on address very much. Yeah.
Any more questions?
Yeah.
Stefan.
For the rare phenomena like the fact that some resolvers reply to a port which is not the port from which the request was sent, did you try to correlate it with the lack of UDP checksum? Because maybe it was simply a bit flip or something like that?
I didn't do that, but that's interesting. Yeah. Yeah, you're right. Maybe it's cosmic rays. Yeah.
One more question. The mic.
I was just going to comment. I wondered or theorized that the responses where the port was different and wasn't 53, whether it was broken CPU devices actually forwarding the response from somewhere else back or just mauling it.
Yeah, it seems to be something like that, or maybe they have NAT enabled, but for some reason they forgot to un-NAT the port and it came out. That's my guess, but given that there's so many, I guess I'm optimistic that we'll be able to nail it down one of these days.
Any more questions? All right, thank you so much,
thank you.
Dwayne. Oh, you have a question, sorry.
Sorry, yeah. Did you try to do any correlation between the the destination you send the query and the forwarder that answer you to see if they were in the same AES or the same network?
I did some inspection of it, and so I didn't do any real analysis or correlation. But when you look at it, just in the log files or whatever, it's really kind of amazing how diverse they are. I mean, there's a lot of cases where you would expect no relationship between these two networks, and that you see that they are somehow tied. So that'd be a cool thing to do for a future talk, is to.
Okay.
Okay. Yeah. You did that. Okay.
Okay. No, I was just curious, but yeah, we can talk.
Any more questions? All right, thank you very much, Dwayne. So this was the last presentation of today. I will pass the mic to Keith. Sorry.
Okay, just a few words of wrap up before we finish. One thing that I wanted to share with you, just bear with me a second. was the proposed dates and location of our upcoming future workshops. Let's get the appropriate slide deck. No, that's the wrong one. Okay, I'm sorry about that. Okay, I did have it on a slide, but it's been a long weekend and I can't find the slide. Thank you. So yes, future workshops will be, we're planning the fall workshop in October to be back-to-back with the ICANN meeting in Los Angeles. So that is the 2 days before the yeah, what I can do is find the dates for you. Excuse me a second. So yes, so the October workshop will be 11th and 12th of October in Los Angeles, hosted by ICANN. In a year's time, we'll be going back to back the right meeting again. This time it will be in Amsterdam, and that's going to be hosted and sponsored by SIDN. And then October 2015, we're going to go back to Montreal. Sorry, we're going to go back and collocate with NANOG on the weekend before the NANOG meeting in Montreal. For 2016, we want to try and plan these meetings out as far as possible. We know you have busy calendars and it makes sense. So for 2016, in the spring, it could be good to go to South America if we can find an appropriate host, maybe collocate with the IETF because it's something that we haven't done yet and we know that you want to do that. These two objectives may not be compatible. And then we've also had a possible offer of India with SANOG in the fall of 2016. So that's the current plan. Obviously, one of the things that helps that is sponsors. I'd very much like one final time to thank our sponsors for this meeting, VeriSign and Microsoft for paying for most of the cost of the meeting, and NZRS and Dyn for the social event last night. There is with these meetings a big long list of people to acknowledge, not just our sponsors. I'm going to miss people out, but I can't name everybody who's helped out. I'd like to thank all the speakers who come here on their own time and expense. I'd like to thank our program committee. It's the first time that we've had a program committee formally for an OARC meeting. We want to continue doing that, especially Sebastian as program committee chair. All our volunteers who helped out. It was great to have so many of you on Friday get your hands on the deck and help out in various ways. Special mention on the volunteer front, George for single-handedly configuring the wireless access points. Dave for enduring the horrors of the Lot 787 fail and doing all the webcasting for us, and Joe for helping out with the webcasting, also for the excellent quiz last night. Thanks to Mehmet at Microsoft for the donation of the Xbox One prize to Team Sexy, who won the quiz. Also like to thank the RIPE NCC. We've tried to keep out their hair as much as possible, but they gave us the wired connectivity, which I think has been excellent and stable. So I know they've been busy all weekend building the right network, so it was great for them to help us out with that. And also the right meeting team who helped us liaise with the hotel and find the venue, and I think also to the hotel. So far I've been a very good experience of the hotel, and also to our AV team as well. So I hope you join me in thanking all of these people for making this meeting possible. So a few final things. Please return your badges to the box by the desk. If you would like to help with the takeout and be our final volunteer helpers, please can you come and speak to me here or Dinesh at the desk before we start ripping stuff up, because we need to make sure the right equipment goes to the right people. Myself and the OARC board will be here for at least some of the rest of the week, so if there's anything you want to come speak to us about, I'm happy to talk to you about that. Videos of the meeting, because we use Google Hangouts, they're actually already on YouTube. But obviously what we'll do is we'll take some time over the next few weeks to cut these up into individual sections. But if there's anything you missed over the past 2 days, then go to the URLs that are linked to from the meeting homepage, and you'll be able to wind through to find the talks that you were looking for. We've had a few people step up and suggest themselves as PC volunteers, but you know, we're still considering that. So if you want to become a new PC member, then, or want to suggest somebody, please do that. And obviously, we would like to find sponsors for the next 3 or 4 meetings that we have. So please speak to Dinesh. He'll be here for the next couple of days as well. And with that, did I miss anything?
I think it would be reasonable to mention the list of the program committee members.
Sure. Yeah, I should have included that in the slide, shouldn't I? Okay. Yeah. Yeah. Well, the program committee members want to stand up and identify themselves, and
Also a special mention to Andrew Sullivan, who couldn't be here, but he also worked with us on the program committee. It seems everything went well, so we are very happy for that, and hopefully we can keep that level of work. Thank you.
Yeah, and of course, you know, happy to take any feedback on how we run the workshops or how we can improve it and do better next time. So thank you all. Enjoy Warsaw for however much longer you're here, and see you next time.
Thank you.
You're welcome. Pleasure.